an equal sign between them, and it's showing that this thing that's on the left side of the equal sign and the thing that's on the right side of the equal sign, that those are equivalent, that they are things that are replaceable. So kind of like if I had my name equals mom, those are interchangeable, right? Because I have my own actual name and then I have the name that my child calls me. Those are equivalent names, sort of. That's not necessarily a great example, but it's this idea that we want to show that this equals this, so we put an equal sign in between and it becomes an equation. So another way of saying that, a statement that says two expressions are equivalent in value. So the warm-up, those sentences or statements were actually giving us two expressions and saying that they were equivalent in value. If you're unfamiliar with the word expression as well, an expression in math is just a collection of numbers, letters, operations that don't have an equal sign. That's the big difference between an expression and an equation. And then equations are kind of a big deal in algebra, so be prepared to see a lot of them. There's so many equations. It's just basically all of algebra just about is equations. Alright, now that we know what an equation is, what is a linear equation? So the word linear there refers to equations that can be represented by a line. So that should be an easy connection to make because the first four letters of linear is the word line. And there's ways that we can tell by looking at an equation that it is actually a linear equation, that we could represent it with a line. And we will look at how the equations go with lines more in the next unit. We'll actually do this thing called graphing, where you make equations show up visually, but we're not quite there yet. We're going to do a bunch of solving first before we get there. So the way we can tell just from the equation that what we have is linear is that it needs to have at least one variable. Otherwise, I mean, I guess it could be an equation if it doesn't have a variable at all, but that isn't an equation that would be very helpful to us, at least not in algebra. So it needs to have at least one variable, but it can actually have a whole bunch of variables, different letters, and still be considered linear. The most important thing about those variables is that they all need to be to the first power. And the interesting thing about that is that when variables or numbers are to the first power, we don't actually write their power, right? So if you have an x in your equation, it's to the first power, even though we don't write that one there. And that has to do with the fact that mathematicians, as well as all of humanity, are lazy by nature, and so they don't want to have to write more than necessary. And the one that is the exponent, as well as the one that would technically be the coefficient or the number in front of x here, we don't normally write those unless we need to write them for our own understanding for some reason. So if you see an equation that just has x without an exponent, it is to the first power. So what would tell you that something was not in fact linear would be seeing something like x with a 2 after it. That would make it not linear. Another thing that could happen is having an x on the bottom of a fraction instead of on top of a fraction, or really anything else that seems particularly weird. Like having 1 over x does not represent something linear. Or having a square root sign and having an x inside of that, that is not something that is linear. So we're just not really going to encounter those things much yet, or maybe not even at all this year. X squared, yes we will. But those other two situations will be a lot farther down the road for us, so that it should be fairly easy, hopefully, to see, okay, x or y or whatever letter I have, since it's not to a power and it doesn't look funny, then this must be linear. And why we care so much about linear equations is they are the simplest type of equations, so we're going to learn about them first. And the rules that we apply to linear equations also are the rules that apply to all other equations, and so it's going to help us build a foundation of knowledge that then we can apply to other types of equations as well. which is really helpful. Also, lines and linear equations come up a lot in the real world. There's tons of things that can be represented with a linear equation, and what's really funny is that whenever people are modeling actually really difficult things that are not lines, they'll sometimes actually still try to use lines to represent them just because of how much easier it is to use lines than anything else. And that idea is that if you have something that's a curve, for instance like the Earth, and you zoom in really far on that curve, if you zoom in far enough, all of a sudden it looks not curved, it looks like a line. So the same idea there, that we can take relationships that are not linear, that are very curvy, and if we just look really, really closely at them, we can still actually think about them as a line. That's probably more information than you needed right now, but that's okay. Let's actually look at some equations. As I mentioned earlier, I've got a website with resources, and so if you would like to be following along with this without having to write everything down yourself, please head over there, link in the description, and you can print off a nice looking notes page for this. It's really important as you're doing math to write things down. There's some muscle memory things that happen that there are studies that show that writing things down and taking notes helps you remember things more than just sitting and absorbing. There's also the idea that you could look back at your notes and use them to help you complete assignments or to study for tests and things like that. And just in general, it's a really good habit. As I go through this, am going to attempt to mimic what I actually would do if I was solving it myself. I'm going to attempt to think out loud and hopefully help you realize what you should be thinking as you do these problems. And so by getting in that mindset of sitting here and writing down as I write down, that can be super helpful. I say all this, and this first example maybe doesn't have a lot to write down because we are starting off with kind of the simplest equations that are possible to solve. So as I look at these, there's more than one way to do this, and I actually want us to use mental math. So just like what we did in the warm-up, I want us to sit and think about the answer. So as I look at A, like point A, like the first equation, which is labeled with an A, it says x plus 3 equals 9. And so in our heads we could think, okay, what's the thing that should be there? Variables are representing a number. We may not know what that number is, but that's the idea. There should be a number where x is that makes this make sense. So what plus 3 equals 9? And hopefully, through thinking about that, you can pretty easily come up with the answer, which is 6. And we'll just go through the rest of these and see if we can do the same thing. So, because it's an equation, actually, we'd write x equals 6 to say, hey, you asked me what x is, and now I've told you x equals 6. On B, a minus 2 equals 10. So there's a number that we should be able to put here that when I subtract 2 from it, gives me 10. So think about it, and if I'm telling you the answer too quickly that you need more time to think, then make sure to pause the video as we're going along. If on the other hand I'm going too slow, there's a cool feature on YouTube where you can speed videos up so that I could be a lot faster if that's what you're into. So something minus 2 equals 10. That should be 12. Alright, let's look up here at C. When these are right next to each other, this is indicating multiplication. So 4 times y equals 20. 4 times what gives us 20? That would be 5. And this last one might be the hardest just because it looks like a fraction, which is intimidating. But what number, when you divide it by 5, equals 6? The answer to that is 30. Now, how difficult those equations were may depend on just how good you are at mental math, or it may depend on how long it's been since you did math, or things like that. But I think most of us who are at an Algebra 1 level of math should be able to, by exerting some amount of mental work should be able to say, okay, I can figure out what number should go where this variable is. But these are the simplest equations possible, and they definitely get harder in such a way that maybe it's not always a great idea to try to just mental math your way through an equation. And so what we have are some really great algebraic properties of equality that we can use to help us figure out how to solve an equation. And they're all very similar. And since you're in Algebra 1, I'm assuming this may look intimidating, this slide, especially the middle where we've got a whole bunch of letters and no numbers. And what I want to encourage you to do is not stress out about whether or not you understand it. Listen though to my explanation, because throughout math, your textbook or maybe the notes your teacher gives you will have things that look like this. And I think the best way to start getting used to and understanding what they're trying to tell you is by continuing to be exposed to these sorts of things, hopefully with somebody there to explain what's happening. So these properties of equality go with each of our operations that we know and love, that we've been learning about for the last however many years that we've been in school: addition, subtraction, multiplication, and division. And each of these properties is actually saying a very similar thing, that if you have an equation, so in all three of these on the middle column it has if A equals B. So if you have two things that are equal, then the next part is a little different on each, but each of them is saying as long as you do the same thing to each side of the equation, what you have is still an equation. So think about what that means. If you have an equation and you decide to just put a number somewhere in that equation that wasn't there before, you no longer know that those things are equal. In fact, they probably are not equal anymore, unless you add 0. You can add 0 as much as you want. But because we have these relationships we're showing that this equals this, if I just decide to put an extra 4 somewhere, that completely changes what's going on. What this is saying is that if we do that thing to both sides of the equation, then we still have the same equality as before. And that gives us this last column that can maybe be an easier way to think of it. So the addition property of equality says you're allowed to add a number to both sides of the equation. The subtraction property of equality says you're allowed to subtract a number from both sides of an equation, and so on and so on. There are other properties of equality as well, I think. I feel pretty confident about that, but these are the ones I wanted us to look at least right now. So now that we've talked about this, we're going to go back to that example and we're going to think about how can we use these properties to solve instead of just using mental math. So those algebraic properties of equality can help us here by helping us figure out a way to actually isolate the variable that's happening. That's a word that we use a lot in math. We want to isolate or solve for the variable. We want to get it by itself on the side of the equation it's on. So here's the algebraic way we do this versus as opposed to the mental math way we did it before. I look on part A and I say x plus 3 equals 9. Because I have x plus 3, what would be super helpful would be if I could subtract that 3 away. That would be the opposite operation to plus 3, and plus 3 and minus 3 together make 0, meaning there will no longer be a plus 3 on this side. So depending on your teacher that you have, which is me right now, they might write this different ways. Because I'm lazy and don't like to rewrite things, I write minus 3 underneath right here. I say I'm lazy and that's why I do it, but I also like the way this looks. The properties of equality say if I minus 3 over here on the left side of my equal sign, I better also minus 3 on the right side of the equal sign. And then I like to draw a line underneath that. Then we do this thing that I think a lot of people find super satisfying. We say plus 3 minus 3 is 0, so we are going to just mark through those. They're not there anymore. That leaves me with just x on the left, because that plus sign wouldn't need to be there either. You could write x plus 0, but that is writing more information than you need, because if you add 0, it's still x. So this would be x equals 9 minus 3, which is 6. Is that the answer we got before? Probably. Yeah, that's what we got before. And if you think about what you did mentally to figure out that you said what plus 3 equals 9, whether you thought about it or not, you came up with that with the idea of subtraction in mind. You had to say, okay, I've got 3 and I've got to get to 9. What's the difference between those two numbers? Difference, by the way, is a word that means subtraction. So, x equals 6, and we did that using algebra now instead of mental math. Whoops. Alright, let's look at b. So here we have a minus 2 equals 10. So because we have a minus 2 there, now wouldn't it be great if we could add 2? So this is a situation where, hey, wouldn't it be great if we could add 2, but oh wait, we can if we use the addition property of equality. So I can add 2 here, and I can add 2 there, here are 2, there are 2, everywhere are 2, 2. I'm so sorry that I have a 3-year-old and you get nursery rhymes instead of rap songs right now. But I'm not sorry I have a 3-year-old, but I'm sorry that that's coming out in this video. Love you, 3-year-old. 10 plus 2 gives us 12, which is the answer we got earlier. And so I said earlier, as I'm going through this, I'm trying to mimic what I think you as a student should do. So these things I'm writing down, we call this showing our work. And yes, earlier we were able to just write down our answer without having to write anything else out. But by writing these things down I'm showing other people who look at this what my logic was. And so what's cool about this is it lets teachers or parents or whoever is looking at your work, it lets them see if you get it wrong, if there's a good, like, why did you get it wrong? So if you wrote down your work here on B and then said A equals 13, everything else was right, you just wrote 13 instead of 12. Well, that's an issue with, you need to be more careful about adding 2, because 10 plus 2 is 12, not 13. Whereas if all you do is write down the number 13 without any other work shown, then the teacher or parent or whoever's looking at it has no idea why you picked the number 13. The number 13 could have just been a completely random guess on your part, for all they know, if you don't show work. So teachers go on and on, math teachers go, and science probably, go on and on about showing work so that they can help you basically understand things better. And also it makes it look less like you just copied down answers from your friend. So 2 good reasons to show work. Part C. So earlier when we did this, we said this is multiplication. 4 times y equals 20. The opposite of multiplication is division. So we were going to use the division property of equality to divide both sides of this by 4. And get y equals 20 divided by 4. Again, this is essentially the same thing we did earlier. We just did it in our head earlier. When you think 4 times y equals 20, you are basically thinking either about your multiplication tables, or you are thinking, okay, well, I'm basically dividing by 4. So 20 divided by 4 is what? It's 5. So we were doing the same thing, just we maybe didn't realize that that's what we were doing. And then on this last one, which again, for whatever reason, I know that fractions just naturally have a tendency to seem scarier than other things. What's happening when we have a fraction is division. And so if we're doing n divided by 5, what we want to do to get rid of that 5 from the bottom is multiply both sides by 5. And so I left myself a small amount of room here to write times 5. But we're going to use the multiplication property of equality and do it to both sides of our equation. So what's really happening is that this is 5 over 1. And if you remember how to multiply fractions together, these 5's cancel out. And that's why that's the helpful thing to do here. And that means n equals 30. So that would be our answer. Okay, now it's your turn to try. So let's see if you've got the hang of this, or if you need more explanation. And it's totally fine, by the way, if you need more explanation. People get things at different rates. What's important is that you keep with it. What we're trying to do here is we are trying to internalize these equation rules so that they become second nature to us. And that requires you doing enough problems to be able to say, oh yeah, I feel like I've gotten the hang of this and know what I'm doing. And the only way to know that is to actually try problems and then find out if you're right, preferably immediately instead of having to wait a while to find out. So pause the video and give these a try, and then start the video back up when you are ready for the answers. Assuming that you did what I asked and paused the video and now have the answers, I'm going to go through and show my work and show how we use the properties of equality to get the answers to these. So 7x equals 21. I'm going to say, well, 7 times x is multiplication, so let's do divide by 7 on both sides and get x equals 3. And again, that's totally reasonable if you knew the answer without having to show any work, especially because I think these in particular, if you know your multiplication tables well, are really easy to do in your head. 7 times what equals 21? 3. I know that. No big deal. Let's look down here at B. So A divided by 2 equals 8. So I'm going to times by 2 on both sides of my equation so that it gets rid of that 2. I'm left with A equals 16. Let's look at C. We have y minus 3 equals negative 10. So since it's minus 3, I'm going to do the opposite and plus 3. And if that's giving you trouble, just know that minusing 3 from minus 3 doesn't make it go away. That's why we're adding 3, is because negative 3 plus 3 equals 0. And that means that we don't have to write a number over here at all. We just get to write y, which is the whole point of what we're doing, is trying to get y, or whatever letter it is, by itself. Now, negative 10 plus 3 involves us having to know how to work with positive and negative numbers. And if that's something you struggle with at some point in time, if not as this video is uploaded, I will have some videos to help with that you should go check out, because adding and subtracting and multiplying and dividing positive and negative numbers is going to be really important to understand how to do, starting in Algebra 1 and continuing on up. So negative 10 plus 3, the idea here is that they're different signs, so we actually subtract the numbers. 10 minus 3 is 7. So in other words, these numbers, if we ignore their signs, are 7 apart. But then where their signs come in is that the bigger number, the negative 10, means that this should be a negative 7. So there's lots of different ways that we can go about trying to understand how to add and subtract positive and negative numbers, but that's really a subject for another video. And then finally D. Again, this could be really easy to figure out in your head. And sometimes when we figure it out in our head, it makes it even harder to actually think about the work that would be required to do it. That if you already know the answer, you may be like, I just don't even know how I would do anything other than what I already did in my head. And so in that case, we have to just sit and think about what's happening here. 5 plus n, those are being added together. And so I want to find a way to make the 5 go away. So I will subtract the 5. And because I want to do that on both sides, I maintain my equality. 6 minus 5 is 1. There is one other thing that I want us to look at on this video that is loosely related, and that's this idea kind of from the warm-up that we can take words and translate them into math, and we could also do that the other way around as well. Okay, here we have a table that shows us some words that we normally connect with the different operations or symbols in math. So addition, the common ones are plus or sum, S-U-M, but also the phrase more than can also tell us to do addition. Subtraction has minus, difference, and less than. Multiplication has times, as in 7 times something. Product and of. Division divided by quotient. Ratio, which I really don't feel like ratio happens a ton. It feels really weird for me whenever I try to put it into something most of the time, so I did do that, as you can see on number 3 here, but I don't think that ratio comes up anywhere near as much as these other words. And then to show equality, we really tend to use equals or is. So we're being asked here, can you write the following words as an equation? It doesn't ask us to solve the equation. It doesn't ask us to say what the number is. It just says, can you put this in an equation instead of it being in words? So a number plus 5 equals 12. Well, we've got plus, which we know means addition. We've got equals, which we know means an equal sign. 5 and 12 are numbers. So really it's just, what do we put for a number? Well, we're going to put a variable, and that's what's going to make this an equation. So a number, I can pick whatever letter I want, but since it says a number, I like to pick N because that's the first letter of number. So a number plus, so I put plus 5 equals, and then 12. What's really cool about this is that typically things go in the same order as what they are in the sentence. The only one that you really have to be careful of is less than. Less than is actually a thing that turns it around. More than technically does as well, but addition can be done in whatever order. So less than is a bit tricky to work with, but all the other ones, it's in the same order as what you would normally have. So that's helpful. Number 2 says 6 times a number is 24. So we write down the number 6. We say times, that's multiplication. We could put a dot here. I don't recommend putting an X for multiplication anymore, just because now we actually use X to mean X. 6 times number, or we could just put the N right next to it. So 6N is tells us to put an equal sign, and then 24. And you probably are looking at these saying, I know what N is, and that's great. I'm glad. It doesn't ask us to do that, but I'm glad that you know what N is. The ratio of a number and 4 is 7. So ratio is a word that means division, or it's also a word that means you have a fraction. And so there's 2 ways of representing division, technically. You can use the divided by sign, but especially starting in algebra and going up, we use the division symbol much less, and we usually prefer to do fractions. So the ratio of a number and 4, we want to have a variable and 4 in a fraction. So n over 4. And we put it in the order that they gave it to us. That equals 7. So we can see how it's almost like math is its own language. We translated English into an equation, and so that word translate, has to do with languages. There definitely can be times where, for whatever reason, you might feel like your teacher or somebody else that's talking about math is just speaking an entirely different language from you. And so it's things like this that help to bridge that gap, that these words have a direct relationship to math or vice versa. So, alright, now I've got a challenge problem for you right before I wrap this video up. I want you to think about this, and it's going to directly lead into the next lesson that I put up, which is solving 2-step linear equations. So think about it and see if you can come up with the answer to this. The sum of 2 times a number and 7 is 11. What is the number? Take as much time as you need. If you think you have the answer, feel free to leave a comment below. Or if there's anything in the video that you didn't understand and would like more explanation on, leave a comment. If you just really want to say hi or brag that you're the first person to comment, that's also acceptable. But definitely let me know what you think, and I look forward to continuing this Algebra 1 journey with you. Hey, thanks for watching all the way to the end here. There is one more thing that you should probably do at this point, and that is practice the skills that were in this video. So I've got a couple options for you. Both of them can be found at my website, kstevemath.com. The link is in the description to get directly there, or you can use the web address on the screen right now and navigate to Algebra 1 and to one-step equations and go through that whole process. Also, a really cool thing I'm doing starting this fall 2020 is a online Algebra 1 course, so that you can actually take Algebra 1 with me online. If you're interested in that for yourself, or if you're a parent and you're interested in that for your kids, please head over to my website and check that out as well. It's important to practice math skills, so I've got a nice little app that generates problems and answers and will also give you some help along the way. I've also got a practice sheet that you can use and just so much more. I'm adding more to the website every day, or at least trying to. So again, thanks for watching. Please feel free to like or comment or subscribe or all three, and I'll see you in the next video. Hi, welcome to a new video. We're in Unit 1 still, solving linear equations on Lesson 2. And since this is Lesson 2, if you haven't already checked out Lesson 1 for this unit, you might think about going back to it. It was some pretty simple stuff though, so you might be able to get away with skipping it. Just watch the video, I guess, and see if you're lost or not. So this video is going to be solving two-step linear equations. So there's a little bit more complexity to it than what we did in the last lesson, which were one-step equations. But because we already kind of got a foundation of some skills in the first lesson, we don't have to focus so much on the foundation as much as building off of what we did and say, okay, how does this apply now to something more complicated? And that's actually a lot of what math is saying, well, we've been doing math, right, since we were old enough to start counting. How do we take what we know and add a little bit more complexity to it? So let's give this a try. The very first thing we want to do here is warm up. We want to get our brains in a math mindset. And so I've got three problems here that are relatively simple. They are attempting to get you to think about order of operations, which you'll see why that's going to be important in a little bit when we start looking at our problems for today. So if you haven't already, you can head over to my website, link in the description, and print off a notes page that has all of this written down for you so that you just have to fill it out. If you don't want to do that, grab a sheet of notebook paper and write stuff down as I go through the video. But either way, go ahead and pause the video and try to do these three problems and then press play when you're done, and we'll see how you did. All right. So order of operations, you might have heard of a mnemonic device called PEMDAS, P-E-M-D-A-S, or perhaps the phrase is what you remember, please excuse my dear Aunt Sally. And that is a mnemonic device we use pretty commonly to talk about order of operations. The P stands for parentheses, we do parentheses very first, or other grouping symbols very first. E stands for exponents, so if we have any exponents, we do those next. And then M and D stand for multiplication and division, and then A and S stand for addition and subtraction. And so the thing that we want to really cement in our minds is this idea that when things are being multiplied together or divided together, there is a connection between them that weighs more than addition or subtraction. It's a weightier connection. What I mean by that is on this first one, we have 4 times 5, and then we have a minus 3. And so this connection between the 4 and the 5 with multiplication is stronger than what's happening with the minus 3. If we think about it like that, it can make it easier to tell what you're supposed to do first. We are supposed to do 4 times 5 and then subtract the 3. So we do 4 times 5 is 20, and then 20 minus 3, which is 17. And that would be our answer. You get a different answer if you do it the other way around. If I do 5 minus 3, I get 2, and then I times by 4, I get 8. So we have to have a way that we all are going to do this to get the same answer. That's why this is the accepted way of doing it, and you don't get to just make up what you want to do. Sorry about that. So the same thing is true for division. Multiplication and division have the same kind of weight, and very rarely actually from here on out will you see many division signs. Kind of regret putting this one in here because normally it's written as a fraction instead. So it actually would be more likely that you would see this written as 8 over 2 to show division, and to me that makes it even easier to tell that the 8 over 2 is supposed to happen before you add the 7 onto it. But either way, understanding that division has to come before addition means that I'm going to do 8 divided by 2 first. So 7 plus 4 and 7 plus 4 is 11. And then this last one, parentheses are supposed to be an eye catcher. It's supposed to be in math, it's supposed to be do this thing first. Take care of what this is. Try to get rid of those parentheses so that you can do the other things around it. So we have 5 minus 9 here in parentheses. So whereas normally we do subtraction last, we're going to have to do it first because that's the operation inside the parentheses. Now, if you are familiar with the distributive property from pre-algebra, we could use the distributive property if we wanted to, and we should get the same answer if we do that correctly. But I'm just going to say, all right, parentheses, 5 minus 9 is negative 4. So I'm going to do 4 times negative 4. What's kind of weird is a lot of times we will put negative numbers in parentheses still. Part of that has to do with when we type things into the calculator, how we need the calculator to understand that we're talking about a negative number. And part of it, I think, just has to do with how nice it looks. Like not having parentheses here and writing a multiplication symbol and a negative sign next to each other, no, gives me the heebie-jeebies. So those parentheses don't mean necessarily do this first. It means, hey, this number together is negative 4. And so now we're free to do our multiplication. 4 times negative 4 equals negative 16. Now, what does this have to do with solving two-steps equations? I'm glad you asked. Real quick, let's remember something from last lesson. We talked about the algebraic properties of equality. These properties say that we are allowed to add things to both sides of an equation and have it still be the same equals relationship. We can subtract things or multiply things or divide things. As long as we do the same thing on both sides, it's okay. That our equation is still an equation. It's still a true statement that the left side equals the right side. So for our one-step equations that we had last time, we were able pretty easily to work through the mental math of what the answer would be. But as soon as we start adding something else to it, another step, it becomes more difficult. The more things you have to keep track of in your mind at the same time, the more likely it is you'll lose track or make a mistake or things like that. So these first two equations that are on my screen are one-step equations because we only have to do one thing to solve. And if I'm using the algebraic properties of equality, on this first one, it's 3 times x, so I want to divide both sides by 3 and get my answer, which is x equals 4. On the second one, since it's x plus 6, I would subtract 6 over to the other side and get x equals 5. But if I look at this last one, can you tell why this is a more complicated equation? There's actually 2 operations happening over here on the left side to x. And order of operations is going to play a part in how we decide to do this. There's a 4 in front of x that's being multiplied by x. And that 4 is going to move to the other side using division. The negative 5 also needs to move away. And that's going to require us adding 5. The question is, which of those do we do first, or does it matter? And I hate to break it to you, but it absolutely does matter. And it has to do with when we are adding something on both sides and when we're dividing by something on both sides, and the way those work. So when I add something on one side or the other of an equation, like if I add 5 here and I add 5 here, I'm choosing to write that add 5 under the minus 5, but another way that I could write this is I could leave a space right here so that I could say I'm going to add 5 at the end, add 5 at the end. And it's just that we get to choose to do negative 5 and plus 5 together, so those cancel out and we're still left with 4x. If I instead decided to divide by 4 first, if I divide all of the left side by 4, that's going to look like this. If I do that right away, if I divide all of the right side by 4, that's going to look like this. So there's a couple problems here. One, the right side, 15 divided by 4, is not a whole number. Sometimes we can't avoid fractions, but if we can avoid fractions, we definitely want to. So that's one reason dividing by 4 doesn't necessarily seem like the best option at the beginning. And then secondly, dividing 4x and minus 5 by 4 means both of those things have to get divided. The same is true when we use multiplication. If there's more than one thing on one side of our equation and we're choosing to multiply, we have to distribute that number to both things. So because of this, we create kind of a special order of operations for solving equations that's actually backwards from what we would normally do with numbers. That if something is being added or subtracted next to x, we want to move that first and save the thing that's being multiplied or divided next to x as last. Because again, think of it like that relationship is weightier. So having 4 times x, those two things stick closer together than the minus 5 does. So we're allowed to move the minus 5 first, and then we take care of the 4 after. It's a little tricky, and that's one of the reasons why practicing is so important, where you're able to tell pretty quickly if you're doing it right. Because the hope would be that with enough practice, your instincts would be correct as far as what you choose to do first. If you're not doing enough practice to know when your instinct is right, then you don't know whether or not to trust your instinct on what you should be doing. And so that's a problem, obviously. So you want to do practice with somebody or with answers nearby so that you can really figure out, okay, is what I feel like should happen actually happening? And if not, how do I make the feelings be right? I know it's kind of weird to talk about feelings in math, but that's really what we've been doing since we were itty-bitty kids, is we are counting, and that counting becomes something, those numbers become something that we know inside of us, right? Not really in our heart, in our brain, whatever you want to call it, but there's a point at which you stop having to pay attention to counting. The same is going to be true here. There's a point at which hopefully we don't have to pay a ton of attention to what we're doing when we're solving equations, because it's just second nature to us. But we have to do a lot of practice to make sure that that happens. Alright, so to give kind of my best summary for how is it that we choose to do things in an equation, what's a kind of universal rule, hopefully, that I can use to know what to do, is you want to think about x like it's the center of what you've got, and everything on the same side of x is surrounding it. And the things that are the farthest out from x are the things we're going to deal with first. So, kind of I mean that in like a literal distance sense. So if x is my center here on this equation, then the 4 is closer to x than negative 5 is. So if I take that negative 5 and move it away, then all of a sudden 4 is the closest thing to x. So this is one kind of strategy that you can use that should also help once we get to more complicated things as well. That we want to work from the farthest things from x first into closer and closer to where x is. So I'm going to add 5 to both sides, which I guess I don't know if we actually, did we solve this on the previous slide? That was 2 minutes ago, but I don't remember. And then we would divide both sides by 4. And notice how I'm showing my work, and that is going to let somebody else looking at this hopefully follow along and maybe learn from what I'm doing. Or if it was my teacher that was looking at it, then if I made a mistake somewhere, they'd be able to tell where that mistake is. That's not to say that you aren't capable of adding 5 and then dividing by 4 in your head. Lots of people are capable of that. But your teacher can't read your mind, and so they don't know if you just put an answer, if you guessed, if you copied off of somebody, which of course you didn't copy off of somebody, that would just be rude. Or if you got it wrong, they don't know why you got it wrong. So make sure you're showing your steps. It's super helpful. Alright, let's do some examples of these. We've already technically solved one together, so we're going to solve a few more together, and I'm going to try to mimic for you what you should be doing, and also try to think out loud for you so that you know kind of the thought process that's supposed to be happening. So we've got 7x plus 9 equals 44, and that looks a lot like what our previous example looked like, our very first two-step equation that we saw. So we have this idea that the 7 and the plus 9 both need to move away from x, so that x is by itself. So choosing which of those is going to happen first, or another way of thinking about it is choosing which should happen last, is really important here. This 7 that's in front of x, anytime you have a 7x like this, that they're right next to each other, that 7 is the very last thing that you want to move. So I'm going to subtract the 9 from both sides first and get 7x equals 35. And then I'm going to take that 7 and divide it on both sides. So you can see that in both of these cases I'm using algebraic properties of equality because I'm doing the same thing on each side of the equation. And I'm also showing my work and making it really neat, boxing my answer so that anybody looking at it can be like, oh, I can see exactly where your answer is. Especially if you have messy handwriting, that can be super helpful. So let's look at B. 2y minus 1 equals 7. What letter is being used in these equations doesn't really matter. I personally, and most math teachers have a few letters that we prefer over others. I honestly would rather just use x all the time, but I know that that's not helpful to have you be stuck in that rut as well. So y is also a nice variable. We do avoid certain variables because they look similar to other things like numbers, like s looks like 5, especially my s's and 5s look similar. But anyway, it's just the same as if we had x. We're just saying y equals something instead of x equals something. So again, I look at this and I have to decide, what am I going to move first, the 2 or the minus 1? I'm going to choose the minus 1. And by the way, if at any point here you're like, well, I think I got the hang of this, you should definitely either work ahead, and then whenever I catch up to you, you can know if you're right or not, or pause the video and work it out and then continue the video to see if you're right. But it's actually, as long as you're not annoying to your teacher about it, it's actually a really good skill to develop where you are listening still to what's being said, but working ahead to see if you actually understand what's happening. Now, one of the tricky things about math notes, I know this happens in mine a lot, is usually there are tricks that are introduced along the way. So it may be that you can already, if you printed off the notes page for this, you already see the next problem, and maybe there's a trick to it that we haven't talked about. So you might get hung up and feel frustrated about that. You'll just need to be patient and wait for me to get there, which is going to happen really soon. See, these look different than the ones before did, and that's fine. It may be that if you look at these, you might be like, oh, I think I know what to do. And that's great. That is a math kind of mind at work to see if what you already know, if you can apply it to kind of a new situation. That's a great skill to have. But I also want to encourage you not to be super frustrated if you don't know how to do these yet, because they're a little different. And so you should know how to do them after we go over them, but not necessarily before. So if I have 3 times and then a minus 2 is in parentheses equals 12, and I want to solve this, there's 2 ways I can go about it. And one of those is using the distributive property, which you probably learned in pre-algebra. And that's where you say this 3 is multiplying a and negative 2. They're both going to get that 3. So you multiply them both, and then you don't have to have the parentheses anymore. That's one way to do it. The other way is to kind of look at both sides of the equation and decide if it would be helpful to divide by this 3 initially. So earlier I talked about when I divide on both sides of my equation, I have to divide the whole side by whatever it is. That's why we said it wasn't the best option before. But here, the thing closest to a is actually the minus 2 because of the parentheses. If we knew what a was, we would do that minus 2 first and then times by 3. So working backwards, it makes sense actually to divide by that 3. Now here's a tricky thing that I think can be hard to grasp. When I divide this left side by 3, these 3's cancel out, and nothing actually happens to the a minus 2 inside. It just gets to be a minus 2 now without parentheses. And I think it's really cool that that's the way this works. It makes it really easy. The times that I don't recommend doing this, dividing by 3 first, and instead doing the distributive property, would be if when you divide by the number it gives you a fraction, because then we want to just wait as long as possible to get a fraction. So distributing would actually make that happen later on. So Now that that 3 is gone, I can take this minus 2 and add it to both sides. And if this is confusing to you, definitely feel free to leave a comment and I can try to do a better job of explaining. Or look at what we did on some of the previous problems and look at how this problem looks and see if you can understand what's the difference here. Why would we do this one different than what we did before? What do you notice that is very different about it? And it's the parentheses that are making the big difference here. So here our answer is a equals 6. And this next one may look intimidating because of this fraction, but again, we want to think of this n divided by 2 as being kind of stuck together until the very end. So that 6 is what we want to move first. So I would subtract this 6 because it's a positive 6. I'm not sure what happened with my subtraction sign there. Subtract 6, which gives us n divided by 2 equals 4. And then remember from the previous lesson how we fixed the fact that there was an over 2 or over whatever, is we use multiplication, because this is just saying n divided by 2, so we need to multiply both sides of our equation by 2 so that it cancels out. And that gives us n equals 8. So that's our answer. Pretty cool. Now it's your turn to try. These 4 problems are going to be really similar to what the 4 problems we just did, and if you need to look back at those examples as you work through them, then that's perfectly fine. That is a math skill, to be able to look at a problem that's similar and to be able to mimic what's happening. If you just start it but get lost and have to wait for my explanation, that's fine too. Just at some point, hopefully, you need less and less help as you're doing these problems. So pause the video, see what progress you can make, and then start the video back up and I'll work through them with you. Okay, so on this first one, there is a little bit of difference here, that our x is on the right side of the equation. I don't know if I'm mirrored or not. X is on the other side of the equation from what it has been. But that's okay, we're still going to move things away from x. There is actually a property that we can use where we just switch the equation around. If it would make you feel better, you can just say, I would really rather this be 3x minus 7 equals 2. You just pick the sides up and swap them, and you're allowed to do that. So if that makes you feel better, go for it. But I'm not going to do that. I'm going to pretend that didn't happen, and I'm going to work with the original equation. So this minus 7 needs to go first by adding 7. So 2 plus 7 is 9. And then we just drop down the 3x, and then that's our next thing we need to do. That 3x says, hey, we need to divide both sides by 3, and 9 over 3 simplifies to 3. Now a lot of these have been giving us some really nice whole numbers, in other words, not fractions. Sometimes our equations give us fractions, and we just kind of have to live with that. Fractions are a thing. In fact, in the real world, fractions probably happen at least as often as whole numbers. If you've ever tried to measure a piece of furniture, then you probably are aware of how infrequently it's a whole number of inches, for instance. Okay, anyway, B down here, so this has parentheses. You're welcome to distribute and try to do it that way. Or if we say, okay, well, 36 divided by 4 is a nice number, we could just divide both sides by 4. So that cancels these 4's out. 36 divided by 4 is 9. And then we write in minus 5. And now I'm going to get rid of the minus 5 by adding 5 to both sides. So 14 equals m is my answer. Let's look at part C. So here's the fraction again. We remember we want to save the y over 5 for last. I'm going to subtract this 1 over. And this is bringing up our positive and negative skills. And so if you are struggling with how to add and subtract positive and negative numbers, that's definitely something you should work on. And as soon as I've got a video to help with that, I will link it in the description, but that might not be right away. So you can check it out, or maybe a little thing will pop up at some point saying, hey, I got a video that will help you with this. Either way, right now, -2 plus -1 is the easiest way to think of this. That the other way is to think -2 minus 1, that's fine. But I just like to think of this like it's always addition. And then the rules are pretty simple. -2 plus -1, they're both negative, so they become more negative. You add them together, but you keep the negative sign, which gives you -3. And then this 5 on bottom, we need to multiply both sides by 5 to get rid of, so y equals -15. Ta-da! And finally, 1 plus 4x equals 17, so we want to look at what's farther away from x, which is this 1. Let's subtract that 1 over to the other side, and then divide both sides by 4, and get x equals 4. Alright, how'd that go for you? Good? Bad? Somewhere in between? Feel free to leave me a comment and let me know how things are going for you. Check out my website, which is on the screen, or if you would like to go to the description and go to actually the web address for specifically this lesson, I've got some resources on there that you can use. This is all going to be a part of my Algebra 1 online course that I'm offering this fall, and hopefully many falls in the future as well, that if you would like to be able to actually interact and get help, there are options for that. You just need to go to my website, kstevmath.com, and get signed up for that. I'm really excited about it because I love teaching and I love interacting with students, and knowing that I am helping people who might otherwise not have a great math experience have a hopefully great math experience. So thanks for watching, and I'll see you in the next video, but make sure to subscribe, maybe do a like, comment, tell me your favorite color, because I didn't leave you a challenge problem here. I'll try to make sure to put a challenge problem in the next one so you have something to comment about. Thanks. Bye. Hello, it's K-Steve Math again here with another Algebra 1 video. So we've gone through solving one-step equations. We've gone through solving two-step equations. You may be asking yourself, is it now time for three-step equations? And my answer is kind of. I guess if there are three-step equations as like a class of equations, that this would be what we would call them, but really after two-step we just call them multi-step. And so today specifically what we're going to look at, you can see on the screen, is solving equations where there's a variable on each side of the equation. And so once we add this to our solving equations tool belt, we've really just got kind of one more way in which we could make these linear equations more complicated, and at that point we just call them multi-step equations. And that's partially because one step, two step, and even this lesson, there's kind of a best way of doing these equations for the most part, not always, but there's kind of a best way to do it. Whereas with multi-step, you could maybe do it in 3 steps or 5 steps depending on your approach. So that's why we had just used that word multi-step instead of 3-step and 4-step and 5-step. That would be kind of ridiculous to name things like that. Anyway, let's warm up first and get a feel for what it is we're going to be required to do, since there's going to be a variable on both sides of our equation. Before we get started on the warm-up, if you aren't already aware, I have a notes page to go with this that you can get off of my website, kstevmath.com, link in the description. That way you don't have to write down every single thing, and just having kind of a notes outline to help you as you're learning how to take notes in math can be really helpful. Can help you organize your thoughts, your notes, and all of that. So if you need to pause and head over there and print it, that sounds like a great idea to me. This warm-up, I picked the topic here because it's going to be important to us as we're solving these equations. It is a concept that you should have seen prior to now in your pre-algebra class. And so if it's not seeming familiar to you, that's fine. That's why we're going to go over it. If it does seem familiar to you, then pause the video and give it a try, and then start it back up so that you can see how you did. So on this first one, 5x plus 7x, we are being asked to add like terms, basically. That's what we call these things. 5x here is a term, and 7x is a term. And if you were watching one of the video before this about two-step equations, it can be helpful to think of this idea of like the 5 and the x together are a thing, and the 7 and the x together are a thing. And it also can be helpful to think of it like an x is a unit or an actual thing, that you're saying, I have 5 xylophones, and I'm going to add to that 7 xylophones. And how many xylophones will I then have? If you didn't catch why I used the word xylophone, it's, you know, one of the only words that I know that starts with X that would fit in a situation like this. Which, anyway, so 5 x's plus 7 x's. How many x's do you have? You have 12 x's, and depending on, you know, what you remember from pre-algebra, we're not going to put an x squared because we added x's together and we still get x, not something different. We don't drop the x from it. We just add the numbers in front and we continue to use the x next to it. So let's look at number 2. We have 9y minus 3y. Now what could we use for y? What starts with y? Yak. Okay, if we have 9 yaks and maybe we give 3 of those yaks to our friend because we want to share yaks with other people, then how many yaks do we have? 9y minus 3y, you subtract those two terms and you get 6y. And again, on this, it's this idea of like terms. We were able to subtract these because they're talking about the same thing. They're both talking about y's, or they're both talking about x's. If we had a mixture of letters, either by accident because I typed it wrong or on purpose to prove a point, we can't combine those things. Or like in number 3, where we've got some things with x's and something without x's, this creates unlike terms. So in 3, as I'm looking at this, I would look through and say, okay, well, I've got a 6x, I've got this x right here, and I've got this 2x, which we need to think of as a minus 2x. That sign in front of 2x is attached to the 2 and the x. So we can put those x's together, and then we can also put our numbers together, 1 and -5 and +7. But what we can't do is we can't combine x's with just numbers that don't have x's because they're not like terms. This can be a really tricky thing to get at first, but I think once you get the hang of that idea of what you're looking for that's like terms and what's not like terms, I think it ends up being pretty easy. So we're going to add these together, and incidentally, if you are struggling with this, I do have a video which I will link in the description, and also have a thing hopefully pop up right now that will tell you where to go to see it, so that you can practice this. I have a video and I have a little app on my website so that you can practice it and make sure you're good at it if that's something you need. Another thing to mention real quick is this plus x right here is a 1x. We'd put a 1 in front of x right here. This is a 1x. All right, that's a really terrible looking 1, but it is a 1 nonetheless. So we're going to do 6x plus 1x, that is 7x. And then we're going to do 7x minus 2x. We could organize our work here in a variety of ways. We could actually write this vertically, and maybe it's helpful to put the signs. We could do something like that. We could rewrite the x's separately but have them be horizontal. Or we could just look at the problem itself and say, okay, I can keep track of this in my head. So either way, we should be getting 5 x's are left, because 6x plus 1x is 7x, minus 2x is 5x. Now we're going to take the numbers and put them together. So we've got a 1, a minus 5, and a plus 7. And if you think of this as a -5, you can do this in whatever order you want. And what I mean by that is saying that this is 1 plus -5 plus 7 allows us to pick and choose what we want to do. Because subtraction, you have to do from left to right. But if it's addition, I can pick and choose. So I could do 1 plus 7 first and get 8, and then do 8 plus -5, which is 3, because that's the same as just 8 minus 5. If you are struggling with positive and negative numbers, I don't at the time of this video have another video and an app to help out with this, but I plan to at some point, so hopefully something pops up, or hopefully there is a link in the description, because the way YouTube works, I can edit the description and the things that pop up, hopefully for forever. Anyway, so we get 8 minus 5 is 3, so this would be 5x plus 3. So that's how we add and subtract like terms. It's just a friendly reminder before we get started with today's thing, which is solving equations with variables on both sides. Alright, so here is an example of what we're even talking about when we talk about an equation that has a variable on both sides. We're still talking about linear equations, so we shouldn't see any exponents or anything weird going on with our equation that we haven't already seen. But what should look different is that on the left side there's an x, and on the right side there's also an x. And for actually solving an equation like this, they should be the same variable. You shouldn't have a mixture of letters, because that makes things more complicated. We'll get there later, but we're not ready for it yet. So what do I do differently because there's a variable on both sides? Remember that we've got these algebraic properties of equality that we can use. We can add things to both sides. We can subtract things from both sides. As long as we do the same thing on both sides, then we've maintained equality, and so it's allowed. We can, we have to remember what our goal is in an equation. We're trying to get x by itself, and so the issue here should be that, okay, well, we've got more than one x. Which x do I get by itself, or how do I get the x's by itself? And what we're going to do is we're going to start off by putting the x's together, either on the left side or the right side. It actually doesn't matter which one you choose, but we're going to put the x's together as a first step, and then the rest of the equation solving is going to be exactly like what we did in our two-step equations. So like I said, this is basically like three-step equations, because we just have one thing we have to do before they're just like what we've already done. So how you decide which way to move your x's could either be you always do the same thing, and I've got a couple options if that's what you like to do, or you can just kind of decide however you want. That's not really my thing, but I guess some people like to live dangerously. So a pretty accepted practice is to look at your x's, which here I've got 5x and 7x, and to say, I want to put those together in such a way that I still get a positive number. And that's only because we struggle more when we deal with negative numbers than we do when we deal with positive numbers. So if you want your best chance of success here, it would be probably to have as few negatives as possible in real life and in math and in English. But anyway, so if that's what I want to do, then I should move the 5x over to the right side, because if I subtract 5x from both sides, I'll still have a positive number of x's. Whereas if I subtract the 7x over, that's going to give me a negative number of x's. But it doesn't actually matter which one you choose, because the other option you have is just to always move the x over to the left side, and there's actually some value in doing that, because it can be helpful whenever you're dealing with inequalities later on instead of equations. But it's really up to you how you want to do it. You just have to keep track of your numbers and you'll be fine. As long as you're doing it right, you can do it however you want to, which is probably one of the dumbest things I've ever actually said, so I apologize for that. Okay, so I'm going to move the 5x over to the right side. So I'm going to show my work so that you can see exactly what's happening. So I'm going to subtract 5x from both sides. Because I picked the same thing to subtract on both sides, I still have the same equality happening for this equation. That is an algebraic property that I just used, that I subtract 5x from both sides. And whenever I subtract it from each of these sides, all that gets affected are the terms with x's. So for instance, 5x minus 5x is going to be 0 x's, which in other words means 0, which means, hey, these go away, which is why I chose to do that. And it leaves me with negative 9 on the left side. Whereas on the right side, where we've got 7x plus 3, and now we're subtracting 5x, that 5x subtracts from the 7x and does not subtract from the 3. For two reasons. One, they're not like terms, and two, when we're subtracting from a side, it doesn't distribute. We don't have to subtract every single term by 5x. We just have to subtract the whole thing by 5x. And so because we can do 7x minus 5x, that's what we choose to do. and we get 2x. And then this plus 3 didn't have anything that affected it, so it gets dropped down and is plus 3. Now this should look like something we did last video or last lesson, where we're now trying to get x by itself, and we have to decide, do I want to mess with the 2 first or the 3 first, because both of those are on the same side as our x. And we always deal with what's closest to x last, so that 2 needs to be dealt with last. I'm going to take the plus 3 and I want to say, how do I move a plus 3 away from this? How do I make it be 0 essentially? I do that by subtracting 3 on both sides. Like so. And then now that all that's left next to x is 2, I can very easily divide both sides by 2, and I will know what x is. So x equals negative 12 divided by 2 is 6 with a negative, because if one of these two is negative, it makes the whole thing negative. So x equals negative 6. And I personally am totally fine with leaving it like this. We could also flip these around and say it's x equals negative 6. That is I think it's the symmetric property of equality that lets us do that, but it's something that's always true. You can always flip the sides of the equations if you want to. So if you're like, wow, it looks so much better with the x on the left, by all means go for it. This is just in general how we do this type of problem. So now that you've seen one done, it may be that you're ready to go and do it yourself. So I've got more examples to walk through. And if at any point you're looking at one of these examples and saying, I think I know how to do this, feel free to stop the video, give it a try, start up the video when you get stuck or when you're ready to see if you got it right. Because it's really important, and I posted a video recently about how we learn math. It's really important for you to be able to see that you're doing it right step by step. And the best way to do that through the internet and YouTube like this is for you to try it, maybe do a step, play the part of the video with that step and see if you got that step right. And if at any point you are confused about what I choose to do, feel free to leave me a comment below and I'll do my best to answer it as quickly as possible so that I can help you with that. So let's do some examples. Example 1. So if you feel like what we already did was enough for you to understand what's going on, this is a great opportunity, like I said, to pause the video, try it yourself, and then see what's happening once you've got it to a point where you're stuck or once you've got the answer. But if you still need more help, that's totally fine too. Lots of people need more than one example to be able to get something. I would say more than half of people, in fact, need more than one example. So in each of these, my goal is going to be to get the variable on one side, and that's it. That everything else will be on the other side. So here I've got a 6x and a 5x, and I want to put them together. It doesn't matter if I move the 6x over to the right or the 5x over to the left. All that matters is that I make a decision so that I'm not stuck perpetually looking at this problem. So my preference would be to move the 5x over to the left. In general, I like moving things to the left. Like I mentioned on the last one, I do also like getting positive numbers, so there are occasions where I move to the right. But in this case, I'm going to subtract the 5x over to the left side. And 6x minus 5x gives us 1x. You can write 1x, or since there's only 1x, you don't have to write the 1 at all anymore. You can just write x. We're going to drop down the minus 1, the equal sign, and the minus 10. And you need to pay attention to the details here, because if you forget to drop down the negatives or get confused about what numbers you're supposed to be writing down, obviously that can make this go sideways pretty fast. But now, this is a really easy equation to solve, assuming we got the last couple of lessons okay, because all I have is x and this minus 1, and so I just need to add that 1 over to the other side. So plus 1, and I get x equals, what is negative 10 plus 1? Since they have different signs, I actually subtract the two numbers, but because the 10 is bigger and is negative, it makes my answer negative. So negative 10 gets slightly more positive and becomes negative 9. So x equals negative 9. Let's look at B. Now, we're using Y. Both of the letters are Y, which does matter. If one letter was Y and one letter was X, this would be a much different problem. We'll get there, but not today. So I need to get the Y's together. So I could either add 7Y to both sides, or I could subtract 6Y from both sides. Like I said, it doesn't actually matter which one you choose, but if you, like most of the world, prefer positive numbers to negative numbers, then we should add the 7Y over to the right side. Like so. That means I have 4 left right here. 6Y plus 7Y gives us 13Y. And then the 17 gets dropped down. And then I say, okay, let's get this Y by itself. We always save what's right next to Y. This 13 is going to be last. I'm going to subtract the 17 over first, and you'll see a really neat thing happens here, that this becomes negative 13 equals 13Y. And so when we divide both sides by 13, we get negative 1, because 13 goes into 13 exactly one time. But that negative makes our answer negative overall. So this has been example 1, technically 2 examples, right? Because we have an A and a B, so that's 2 problems. I have an example 2 that you are welcome to watch me work through, or you're welcome to try on your own and then check to see what the right answer is. And then after example 2, I also have a now you try. So if you're like, oh, I've already got it, you might skip ahead to the now you try. Whereas if you're still not sure you get it, just keep watching and hopefully you'll get it. For the most part, these examples don't really have anything new and tricky happening, but there is something that happens here on example 2A that you maybe would get thrown off by if you're doing it by yourself. I don't know. And so the idea of, if we want to make things positive if possible, how do I decide whether to move the negative 4A or the negative 3A? Because in both cases I'd add something. You would, if you're just aiming to make things positive overall, you'd want to add 4A over to the right side, because that's going to give us a positive 1A. As opposed to if I add the 3A over, then I'll still get a negative, right? Because 3A is not as big as negative 4A. Like I said, it would not matter. And in fact, just for funsies, let's not do that. So that if you forget or just accidentally add the wrong thing, or you are doing the just get everything on the left side thing, let's see how that would work out on this one. So if we just want to get everything on the left, or the A's specifically, if we want to get the A's on the left side, I'm going to add this 3A over, sorry about that plus sign, over. So negative 4A plus 3A leaves us with negative 1A. You can write negative 1A, or you could just write negative A, which means the same thing. It might help you to write the negative 1 instead of just negative A, but it's up to you. Then I'm going to take this negative 18 and I'm going to add 18 to both sides. If you haven't already noticed by now that this is fairly repetitive, we're doing kind of the same thing every single time. I hope you notice it soon. That is something that's helpful in math, that it's not like every problem is different. You practice problems until they're repetitive and until you've got the hang of it, so that when a new problem comes along that's harder, you already have a basis that's already in the back of your mind that you've accepted as how you do it, so that you're building constantly off of prior knowledge instead of constantly having to reinvent the idea of how to solve an equation. So negative 21 plus 18 gives you negative 3. If you wrote negative 1A equals negative 3, it should be hopefully pretty obvious. Well, I can divide both sides by negative 1, or you could multiply both sides by negative 1, or it could be that you just need to think, well, if I have negative A equals negative 3, then positive A should equal positive 3. However you want to go about thinking through that last step is fine, but we do have 3 kind of ways we can think of it. Dividing by negative 1, multiplying by negative 1, or just saying the negatives cancel each other out and leave us with positives. So that's why I wanted to move to the left to have that last line happen, where what do you do whenever you got a by itself, except that it's negative. You can't just stop and say negative a equals negative 3, because we want to know what positive a is. All right, let's look at b. We have a 4n on the left and a negative n on the right. We want to put those together. So I'm going to move them. I'm going to move the negative n by adding an n to both sides. And in case for whatever reason you decide not to watch the rest of the video, I do want to throw out there for those of you who like to show as little work as possible, which I mean in reality is technically all of us, I want to say, as human beings. You can actually combine the first two steps if you are being careful and feel like you have the understanding too. So what I mean by that is, since I'm adding the n over to the left side and making this go away, then I can know right away that, oh, the next thing I would do is add this 17 over to the right side, and so that we can do those in the same line and save ourselves some rewriting and some room on our paper. If you're like, okay, you totally lost me, that's fine. You may not be ready to do that yet. It's totally fine to show more work, but it's also fine if you're like, I'm getting the hang of this, I can do both of these at once. Eventually, hopefully you'll have done enough of these that you can be like, oh yeah, I can totally do these two things at the same time. It's very much I'm going to move this over here, I'm going to move this over here, and then we're good. All right, so 4n plus 1n is 5n. And negative 7 plus 17 is 10. And then we're just left to divide by 5. And it's actually really cool when we combine those steps because, I don't know, it makes it feel like a lot shorter problem, I think. Because whenever I learn, as kind of a side note, if you're even still watching, when I was in Algebra 1, I remember my teacher talking about x's being like cows, and the numbers being sheep or something, the equal sign being a fence, and you want to get all your cows on one side and your sheep on the other. And so it's this idea of, okay, move the cows over to the left, move the sheep over to the right, and then, okay, now we just got to divide by that other number. I don't know if that's a helpful analogy to you. I found it helpful at the time, but, you know, whatever works for you. We need to get the variable alone on one side and the numbers alone on the other so that we get an answer. And in this case, that answer is n equals 2. The next thing that I've got going on is the now you try. If you've already been trying on your own and succeeding, you can probably skip this part. But if you want more practice where you'll know whether or not you got the right answer and potentially be able to figure out what your mistake was, then please continue to do it. And if you are feeling like you're ready to be done, skip to the end of the video to see what resources I have available to you on my website. Alright, now you try. So we've got 2 more problems that you can try on your own and see if you got the hang of this. Or you can just go ahead and skip to the end of the video to see what resources I have available to you. That's fine too. If you, before I forget, there is a challenge problem. So don't skip too far. Make sure you look at the challenge problem because it's challenging. So I want you to try these and then you can start it up and see how you're doing and see if you've got it or not. Alright, so I'll walk through this with you, and if you made a mistake or got stuck, hopefully you'll figure out what happened and learn from it. So I on A am going to take the negative 3x and I'm going to get rid of it. So I'm going to add 3x to both sides. Then on the next step, I'm going to want to take the number that's on the right and move it over to the left. So I can do that on a separate step, or I can do that on the same step. If I do it on the same step, it should look like this. So that I'm doing negative 12 plus 2, which is negative 10, and 2x plus 3x, which is 5x. So divide both sides by 5, and negative 10 divided by 5 is negative 2, and then we get x by itself. So x equals negative 2. And if that helped you figure out something new, feel free to pause the video and try B if you haven't already. If not, let's just keep going. So I'm going to be different this time, and I'm going to move the 9x over to the left, even though that is going to give me a negative number. If you did it the other way, that's fine. Hopefully either way we'll get, not hopefully, we should get the same answer. whichever way we decide to do it. But if you made a mistake and moved to the right, hopefully you'll still be able to figure out your mistake. So I'm going to subtract 9x from both sides and subtract 14 from both sides so that I get negative 8x equals 22 minus 14 is 8. So I divide both sides by negative 8 and I get a negative 1. So that's my answer. Hopefully you are feeling pretty good about this right now, but there's always more opportunity to practice and get better at it. And definitely feel free to leave a comment if something about this did not make sense to you, or if you think I made a mistake, or if you just can't find your mistake. Challenge time! Okay, so part of math is taking what you know how to do and trying to apply it to something new. So this problem is kind of similar to what we've been doing, but also kind of combines some things that we haven't had combined before. So I want you to give it a try and see how far you can get. If you get all the way to an answer, feel free to comment with your answer below. Or if you get stuck and want to leave a comment about what you tried and what you ended up with, leave a comment about that and I'll do my best to help you get through the rest of it. But if you're just like, I don't even know how to approach this, this is actually the kind of problem, or one of the kinds of problems we're going to be solving in the next lesson that's about multi-step linear equations. So stay tuned for that video. That'll be coming up hopefully, next soon. Thanks so much for watching. Every time you watch one of my videos, I really appreciate it. And if you want to subscribe or like the video or comment, that'd be super awesome. Another cool thing you can do is go check out my website, which is on the screen right now. And I'm adding new stuff to that just about every day. Resources that you can use, or if you're a parent, you can use for your kids, or if you're a teacher, you can use for yourself in your classroom. But in particular for this lesson, if you go to the link in the description that goes specifically to like this lesson on the website, you'll see that I've got the video linked on there, and I've got an app that gives you practice questions and tells you the answer. I've also got a worksheet that you can use for practice as well. So you can go check those things out and hopefully get some use out of them and learn something new. Like I said, thanks so much for watching, and I look forward to seeing you in another video. Bye. Hello there, K-Steve Math here again with another math video for Algebra 1. This is the fourth in my series, and the fourth of this first unit on solving linear equations. And this is really, I think, where it gets the most complicated that we're going to see on solving linear equations, at least for right now. This is called solving multi-step linear equations, and I actually mentioned in the video for last lesson, we did one-step equations and we did two-step equations, and then after that it's not like we just keep calling them three-step, four-step, five-step, and so on. Partially because there are slightly different ways that you could choose to do it, or there are ways to kind of combine some steps, or to take longer with steps, so that it just gets trickier to count how many there are. So that's why they're called multi-step, to imply that there's more than two steps, and you can kind of choose how you want to go about it. In some ways, we are going to have a kind of best ways to go about them that you'll see. And here's your quick reminder that I have a notes page for this that you can print off of my website, which should pop up in the corner, a link for you to get there so you can do that. That way you don't have to write down all of this stuff on your own. You can just fill in what you want to fill in as you're working through the examples with me. I want to start off with a nice warm-up that's going to help us get in the right mindset for doing some of these problems. And if you look at this warm-up, what's different about this than maybe what we've been doing in the past few lessons is we've got some parentheses here. We did have parentheses in one lesson, but in that lesson I talked about how distributing isn't always the best idea, that sometimes dividing by whatever's in front of the parentheses in an equation actually makes things easier. But in this lesson we're going to find that distributing is the right way to go. So I wanted us to warm up and and basically remember how to do the distributive property. So the distributive property says that if there's a number on the outside that is right next to the outside of the parentheses, so it's showing that this is multiplication here, 2 times this parentheses, then that means that all of the things in the parentheses need to get multiplied by whatever that number is. So for instance, I need to do 2 times 3x, but I also need to do 2 times -5. And you'll often see teachers and then students draw arrows to point this out to themselves that, hey, I want to do 2 times both of these things. I think it looks cool to do it, and it also can help you just remember to distribute it to both things. So 2 times 3x, whenever we do that, we multiply the 2 and the 3 together, and then the x just comes along for the ride. Think of it like we're saying we have twice as many as 3x, which means that we would have 6 x's. Remember the xylophone thing? So if I have 3 xylophones and I get twice as many xylophones, I have 6 xylophones. So that's 6x. Then I'm going to do 2 times -5. Make sure you pay attention to the fact that this minus sign is here, and I get a -10. So if you were like, I don't remember how to distribute, and now you remember, you might think about pausing and trying the next one on your own. But hey, no worries, we can go through this together, and that's fine too. So -6, I want to distribute. So I actually like to wait to draw the arrows until I'm actually on that step. So I like to do the arrow and say, okay, I'm going to do -6 times y, since y doesn't have a number in front, which is also known as a coefficient. It just gets the -6. It would be like if we were a 1 there, -6 times 1 is -6. So this is -6y. Now that I'm ready to do the next one, that's when I like to draw this arrow. So -6 times 10 is -60. And the reason I mentioned that is because I can't tell you how many times I've seen students that have the arrows drawn and then did not actually distribute all the way through because they just drew the arrows first and then forgot to follow through. It happens. Don't let it happen to you. Alright, this third one has this -10 at the end that makes it different than the first two. And so this isn't just that we're going to distribute, we're also going to have to add some like terms, which is something that we went over, I believe, in the previous video. So I want to distribute this 5, and then once I'm done, I'm going to -10 from anything that I can, whatever is like terms. And this is where our order of operations matters, because I want to do this multiplication that's happening first before I do the subtraction for 10, because multiplication has a weightier priority than the -10 does. So I'm going to do 5 times -2n and get -10 n, and then 5 times 7, which is 35. And then that's this part right here, so I need to finish by writing the next part, -10. And then I have to ask myself, okay, what can I actually combine here because of like terms? Since we have -10n and there aren't any other n's, it's going to stay the exact same and still be -10n. And then 35 and -10, those can combine by subtracting them, and that gives us 25. And that's our answer. I boxed that one, and now I feel like I have to box the other ones, so that's just how it goes sometimes. Now let's look at what our equations are going to be like. Let's talk about like our best order of which to do things. If you download the notes page and print it off, then you already know what our examples are going to look like, because you can just glance down to the next part of the page. If not, you'll see in just a moment what these equations are going to look like that we consider multi-step. But here's the order that it is best to handle these kind of complicated equations. And you don't always do every single one of these steps, but if you do need to do them, this is the best order to do it, to hopefully not accidentally commit some sort of math error that you didn't realize you were committing. So the very first thing is, if you see parentheses, it is safest, if it's a complicated equation, to go ahead and distribute so that you don't have to keep those parentheses. We did, during the two-step equation lesson, talk about how you can divide by the number in front of the parentheses, but that in these, since our equation is going to have more terms and more numbers and things like that, it's a little trickier and it's less likely to be helpful to try to do that. And I'll show you that on our examples, why exactly that is. So we're going to just first off distribute to get rid of parentheses. Once we've gotten rid of our parentheses, we're going to look at each side individually and say, are there things that I can combine because there's like terms? So we'll look on the left side and say, okay, are there like terms over here? And then we'll look at the right side and we'll say, okay, are there like terms over here? And if so, we'll combine those. Once we've got that done, our equation should look like what it did last lesson, where we will most likely have a variable on each side and a number on each side, because we've combined all like terms. So we won't have more than that, but we should have that on each side. And so once we're there, then it's time to get the variables together, get the numbers together, and finish solving like what we've been doing. So this is definitely a situation where we are building off of what we did before. And so if you start looking at this and you're like, okay, I don't know that I got the last lesson because this just seems super hard, that's where you go back and practice more, or just really try to pay attention, because I'm going to try to explain every single thing that I'm doing, and so hopefully that will help. A kind of quick note about these examples: they are going to get longer as we go and more complicated as we go, so it does kind of build in difficulty, which means that if you're trying to pause and work ahead, that's great, but if you're like, well, this one looks more complicated, I don't know what to do, then that was actually kind of intended. There are still the now you try at the end that are not any more complicated than the examples are before them, so you do have that opportunity to try. Quick reminder, you can speed up the video or slow it down. If you're on YouTube, there's a little gear icon that lets you adjust how fast it's going. So if you're like, man, you are going so slow, you can speed it up, or if you feel like I'm going super fast, you can slow it down. You can always pause the video and catch up on writing if you need to, or even skip ahead if you're like, okay, well, I just need to know what the right answer is. That's the beauty of learning from a video. You have so much control. I mean, you could mute me if you wanted to, although that probably won't help a ton, but you could. You have that power. Go ahead, try it out. See, you can't hear what I'm saying right now, right? Have you turned it back on? I'm going to assume you've turned it back on. Okay, let's do this example. So you can see that we've got parentheses here, and I said in the last slide we're going to do the parentheses first. And before I actually do them, though, I do want to quickly mention the idea of we could divide both sides by this 4 instead of distributing the 4. But the problem with that is that these don't divide by 4 evenly. So we'll have fractions, which are not necessarily a bad thing, but it is something that we actually will be able to avoid if we choose to distribute instead. So that's why distributing is my best option for now. So I'm going to distribute 4 into this parentheses. 4 times 3x is 12x. And 4 times negative 8 is negative 32. And there's not any parentheses on the right side. There's not anything really I can do on that side. So I just rewrite it again. And our next step, which is to add like terms on each side, we don't have like terms. So the 12x minus 32, one has an x, one has a number, so those can't be combined. And on the right side, negative 3x and negative 2 aren't like terms, so those have to stay. We're ready to move on to the third step, which is getting x together and getting our numbers together. So it doesn't matter which way you go. You can go ahead and subtract the 12x over to the right, or I can add 3x over to the left. Remember, I used the opposite operation, so I'm going to add 3x over to the side. And if you're not ready for this, then you can go ahead and write stuff down and then go on. But I feel ready to go ahead and add the 32 over to the right side on the same step. And so that means I've got 15x, because that's 12x plus 3x, equals negative 2 plus 32, which is 30. And now my final step is to go ahead and keep working to isolate this x. So I'm going to divide both sides by 15, and I get the answer x equals 2. So how was that? Not too bad, not too much more complicated than what we did last lesson, but we're going to see that there's going to be more things each of these examples that I do. So get ready for example 1b. All right, here we have example 1b, and we want to go through those steps again. So starting off, our eyes are supposed to be drawn to the parentheses. This time they're on the right side. That's going to be fine. We're just going to take this 3 and I'm going to distribute it here. So 3 times 2x is 6x. Then I'm going to distribute it here. 3 times negative 7 is negative 21. So that's this part of the equation, and everything else around it needs to be dropped down, and it needs to look exactly the same. Just the only thing that should change is the 3 parentheses 2x minus 7 close parentheses. That's changing to 6x minus 21. So I should have this equal sign drop down, this minus 7, this minus x, and on the right side of what I wrote, I should have this plus 14 drop down. So that's the first step, get rid of parentheses. Again, dividing by 3 here is not going to actually be more helpful than what we did, because we would have to not only divide the left side by 3, but we also have something else on the right side that would have to get divided by 3. So really, if you're not sure that you can divide, if you're not sure that you're allowed to divide by the number in front of your parentheses in an equation, then your best bet is probably to distribute instead. So just as a general rule, at least for right now where you are in Algebra 1. Now let's look at step 2, add like terms if we have them. So the left side doesn't have any, that's negative x minus 7. The right side has these two numbers which can be put together. So negative 21 plus 14 is negative 7. So this is 6x minus 7. Our next step is that we want to get our x's together and our numbers on the other side together. So either we need to add x over or subtract 6 over. I'm going to add x over to keep that positive thing I've got going on. Positives are way better than negatives, right? And then that means that I would add this 7 over to this side. But wait, you may be alarmed by what happens, because this plus 7 cancels out there as well, which means we've got 7x, but what does 7x equal? If we get rid of everything on one side or the other of an equation in this manner, then that means that we would have a 0 there, because we got rid of the negative x, we got rid of the negative 7, now we have nothing, but nothing has a number that represents it. Nothing is 0. So now I can say, well, I need to divide by 7, which gives me 0. Now, thanks to, I don't even know when exactly this happens, there's this confusion a lot of times between which of these is okay and which of these is not okay. You are allowed to have 0 on top of a fraction. 0 divided by 7 is 0. You're not allowed to have 0 on the bottom of a fraction and get an answer. We call this undefined. And here's why. 0 divided by 7 is saying that you have 0 of something and you are trying to divide it into 7 groups. So if you take 0 and divide it into 7 groups, each of those 7 groups will still have 0. So it maybe doesn't make a lot of sense to try to divide 0 things into groups, but you can. They each get 0. Whereas if you have 7 divided by 0, it's saying, I have 7 things and I want to put them into 0 groups. Well, wait, you can't take things and put them into no groups. I mean, that means you're not actually doing a thing. So that question just doesn't make sense, which is why we call it undefined. And that's going to be important to us in the next unit, whenever we're talking about graphing and slope and stuff like that. But for now, it's just, if you looked at 0 divided by 7 and were like, I don't know if I can do that, yes, you can. 0 on top is fine. If you haven't asked Siri what 0 divided by 0 is, by the way, you should do that because it's funny. If you have the ability to ask Siri because you have some sort of Apple product. But I don't know, maybe other ones have interesting answers too. So, I mean, by all means, ask Alexa, ask Cortana, ask whoever else there is out there. Here we are in example 2a, and like I said, it's getting more complicated because now we have not just one set of parentheses, but 2 sets of parentheses. So, we're going to distribute on each of these. We're really going to treat this like it's kind of 2 different things we're doing. When I distribute the 4 over on here, like that doesn't affect anything else in the equation. It just affects this part right here. So I'm going to do 4 times negative 5x and get negative 20x. And then I'm going to do 4 times 7 and get 28. And that's everything that's on the left side. So I need to equals. And I'm going to do the same thing with this negative 5. I'm going to distribute it here. It does not get distributed to the 73. It does not get distributed to the 73, which is good because I don't want to do negative 5 times 73. Negative 5 times negative 3x, though, that's a positive 15x because 2 negatives make a positive in math, English, and not in life. Negative 5 times 2 gives us negative 10. And then we put that add 73 at the end. Now, we've gotten rid of parentheses. We check for like terms. The left side doesn't have like terms, but the right side does. I can put negative 10 and positive 73 together. So everything else needs to stay the same. It's important that you pay a lot of attention as you're rewriting. Like I almost just wrote 128 instead of 28, which would have been bad. Because lots of mistakes can happen just from not rewriting the next line correctly. Negative 10 plus 73 is 63. Now I want to get my variables on one side and my numbers on the other. So I'm going to choose to add 20x over here, which makes this go away. And then I'm going to subtract 63 to this side, which makes this go away. Ooh, 28 minus 63. So we actually do it the other way around and have to borrow. So that gives us 35, but it's negative because the 63 was the bigger number and was negative. So negative 35 equals 35x. Well, hey, conveniently enough, that divides nicely. And so we get x equals negative 1 as our answer, because when you're dividing, if one of them is negative, it makes your answer negative. If 2 of them are negative, it makes it positive. If they're both positive, it makes it positive. Okay, this is the final example, and as far as multi-step equations go, this is about as complicated as I think it usually gets. I mean, by all means, we could add more numbers and stuff on each side, another set of parentheses or 2, but I think that for the most part, this is about as complicated as you should see it. And really, even this is going above and beyond what is really truly necessary. If you have a test over solving equations, I would expect that if there are any that are this complicated, there would only be one. And because it's not as easy to they're not as easy to do, they're not as important to be able to do. Most of the equations we end up solving for our word problems, which will be a later lesson, are going to be a lot simpler than this. So it can be a kind of a fun exercise to do complicated equations like this, but at least at this point in our math life, it's not necessarily super duper 100% important that we can do one of these every single time. That being said, you can do this. What you already know, we can apply to this and get the correct answer. We just have to be able to, pay attention and keep track of our numbers and work at it and persevere. So let's distribute on the left this negative 2. Negative 2 times negative 3y is positive 6y. And then let's distribute negative 2 times 5, which is negative 10. That's this part right here, so I need to go ahead and write this plus 5 down. Then I'm going to do this 2 and get 2 times negative 5y, which is negative 10y, and then 2 times negative 1, which is negative 2. And so that's this part right here, so I need to put the minus 51. Now, you might be able to combine some steps here, but you need to practice enough to know whether or not that's something that you can do safely. So practice enough where you can see if you've got the right answer or not. For instance, you may be thinking, well, I already know that I'm going to get the y's together, so I can do that on the same step that I add like terms. I don't suggest doing that. I think you should keep them separate, but by all means, if you feel like you can do that, go for it. I'm going to add like terms. Negative 10 plus 5 is negative 5. So there's like terms, and here's like terms. But the 6y and the negative 10y for now don't change. Negative 2 minus 51 is negative 53. So now I want to get the y's together and the numbers together. By the way, notice that when we're adding like terms, when I do the negative 10 and the plus 5 together, I didn't change the operations happening there like I do whenever I move things across the equal sign. So it's essentially like we're ignoring one half of the equation and saying, is there anything I can just do with this right here to make this simpler? And so that's why we don't have to do opposite operations. Whereas now that we have everything as simple as we can get it, now we're going to have to do the opposite and add 10y so that it moves from the right, and do the opposite by adding 5 so that it moves from the left. That gives me 16y equals negative 48. And then we divide both sides by 16. Now this is a tricky one. I know it's negative because one of the numbers is negative, and I actually know what it is off of the top of my head because of how much math I do. But if you didn't know, or if you don't know, you could just try simplifying this. Like both of these numbers are divisible by 2. So I could say, well, if I divide them both by 2, that gives me negative 24 over 8, which is an easier division problem to do. That gives us 3, or negative 3. And so that can be a way that if you can tell something can be reduced but don't know if it divides evenly, that's a way you can check without having to resort to using your calculator. Since, you know, if you're not allowed to use a calculator in Algebra 1, which lots of people aren't, then using it on your homework isn't helpful if you use it as a crutch, so that you would need it on the test or quiz as well. So just keep that in mind. Alright, we've reached the now you try. So 2 problems here, A and B, for you to try on your own. Pause the video, start it back up when you're ready. If you can't make it through the whole problem successfully, that's fine. If you've got a friend, sibling, parent, other relative, other acquaintance, someone who can maybe help you find your mistake and figure out what you're doing wrong, that's great. If you don't have one of those people but you would like to leave a comment below so that I can try to help you, that's a great idea. But do at least try and see how far you can get, because I feel like you should at least be able to do the first step, maybe even the first 2 steps, or kind of some combination before you get stuck if you've been paying attention. So pause, and then when you start it back up, I'll be working on this problem. That was done. Okay, so first step is to distribute this 3. So everything else stays the same. X minus 4 equals 3 times negative 4x is negative 12x. 3 times 1 is 3. And don't forget this plus 6 at the end. That's an easy mistake to make. Now I look for like terms, which I have some right here. 3 plus 6 is 9. And then we want to get our x's together and our numbers together. If at some point you're doing these problems and you're like, wow, this just feels really repetitive, and you're also getting the right answer consistently, that is a good sign that you have done enough practice, at least for now. You can always do more practice to make sure it sticks in your head. Now I'm adding 4 to both sides, but as far as if it feels repetitive, hopefully that means that you've gone through the steps enough to be like, okay, I can see that there's a pattern, there's a consistency. It's not like I'm doing something different every single time. That's not how it should feel. We're solving equations. It kind of works the same the majority of the time. There are patterns. So then we divide by 13 on both sides and get x equals 1. If you feel like you learned something from that one and have not yet done B, you should try B on your own and then start the video back up and see how it went. Okay, so this one is another one that this is about as complicated I feel like as it gets. So I'm gonna distribute one time on each side and then add like terms and then do all the rest. So if at any point you figure out a mistake you made and want to pause so you can try the rest of the problem again, that's a great idea, because this is the last one of these that we'll do together before I send you off to do these completely on your own away from me. I'm so proud. So negative 2 times 3x is negative 6x, and negative 2 times 7 is negative 14. This negative 5 needs to drop down, and then I'm going to distribute this 4. 4 times 4x is 16x. 4 times 11 is 44. And I'm going to add this 25. Now I'm going to add like terms. So I've got this and this to add together. Not to each other, but like negative 14 minus 5 is negative 19. And 44 plus 25 is 69. And now I'm going to put the x's together and the numbers together. So I'm going to add the 6x over here and subtract 69 over here. And this gives me negative 88 equals 22x. I'm going to divide both sides by 22 and get my answer, which is negative 4. So, how'd you do? That's another thing you could tell me in the comments, because I'd love to know how it's going for you. Here's this lesson's challenge problem. So it looks a little similar to what we've done already, but there is something different that happens here that is likely to throw you off. And if you think you know what to do about it, or if you think you have the answer, please comment below and I will let you know. But if you are just like, I have no idea because this is completely different than what we just did, that's okay. The next video, this is what we're actually going to go over. Is what's going to happen, what happens some of the time. It hasn't happened to us in any of the problems I've done in these videos so far, but it can happen to us, and I want us to address that. So here's your challenge. Give it a shot. See if you can get the right answer, or an answer in general is also fine. Get something. Do something. Finally, thank you so much for watching. I have a really cool website that I've been working on for a while now that I'm really picking up steam on. If you go there, link in the description, or the just general link is on the screen, like probably right above my head right now. If you go there, you can find all sorts of resources. I'm adding resources daily. For this lesson in particular, if you went and printed out the notes page, then you know, are a super cool person for doing that. There's also a practice page you can print out. And there's also this cool app, which probably is appearing on the screen right now, that you can use to give you new problems to practice where you would know what the right answer is. And in fact, I made the app before I made this lesson because I did not want to have to make the problems up on my own. I programmed the app so that it would give me relatively nice numbers that all worked out, and then I just clicked the new problem button and until I got ones that I liked. And so I'm pretty proud of myself there for doing that and using that. And you can use that too. You can go and it's not a put in an answer and see if you're right thing. It's just a, here's a problem, you know, write it down, work it out, get an answer, and then click the show answer button and see if you're right. And that way you're getting some immediate feedback. If you're not getting it right, then you're going to have to get someone to help you, which could be a parent, guardian, sibling, other relation, friend, tutor, or, you know, I haven't mentioned this lately, but I do have a Twitter account at KSteveMath, and I'll put put a link to that or a thing to that in the description as well. If you are ever stuck on a math problem that you need help on, you could tweet me a picture and I would hopefully be able to help you figure out what your mistake is. Unless people start doing that all the time, and then that might take up too much time, but I can try. So like I said, thanks for watching. Please subscribe, please like, please give me a comment, and I'll see you in the next video.
Hello and welcome to a new video. So this is a part of my Algebra 1 series. We're still talking about solving linear equations. This is my 5th video in this series, and it's going to talk about solving special cases and checking answers. And I think both of these things are helpful for those times when things seem to get a little weird. If you'd like to follow along, I have a notes page you can download. Just click the link in the description or the link that hopefully will appear up above my head somewhere around now. Let's start off with a nice warm-up. So hopefully this is a kind of problem that you have seen before in pre-algebra, and so it's not too tough for you to do. But that being said, if you find yourself struggling, just continue watching. If you want to give it a try yourself first though, please pause the video and start it back up when you're ready. Okay, I'm going to assume you're ready. So we're being asked to evaluate an expression in each of these problems, and we're also told that x equals something. So what we can do is we can put what x equals where the x is, and then evaluate means find an answer for, basically. We use that word a lot in math, in like math textbooks or in math worksheets and things like that. Evaluate just means, you know, work with this and try to get an answer. So here's what we're going to do. We're going to take this 2 and put it where this x is. So I'm going to do 2 times 2 plus 5. Now I got to make sure I do correct order of operations here. What I mean by that is that multiplication needs to happen before addition. So I'm going to do 2 times 2 first, and then I'm going to add 5. 4 plus 5 equals 9, and that's my answer. If you got that right, good job. If you didn't, hopefully you learned something. On the second one, if x equals -5, evaluate, and this time we've got an expression that has parentheses. The first step here, if you're thinking about PEMDAS, this kind of adds a step at the beginning. We go ahead and we put in this -5 first because it can change what we're able to do and what order. Because if we don't put the -5 in, you might be thinking, I'm going to distribute, and that's fine. You can distribute, but you don't have to if you plug in the -5 right off the bat. Let's take a look. -9, and then where x is, I'm going to put -5. So I'm going to do -5 plus 1 in the parentheses, which gives me -4. And if you just still wanted to distribute, that's fine. The distributive property works. That's kind of the whole point of it. We just didn't have to use it if we realized we could combine those numbers like the normal way. -9 times -4 is positive 36. Remember, 2 negatives, when you multiply them together, give you a positive. The negatives are like, peace out, I'm going to go play a video game, and you guys can do math without me. So it's positive 36. We got 2 types of problems coming, and so this warm-up is going to actually help us more on the second one than on the first one, but hey, it's whatever. If you watched my video previous to this one, 1.4, then at the end there was a challenge problem. We were solving multi-step equations, and then I left with this problem and I didn't say what the answer is. So now we're going to explore what happened. So if you did this challenge problem, hopefully you kind of remember, and we can talk about, well, not talk about, I'll talk about what's going on. So if I distribute this -5, I get -10x minus 40. Distribute this -10 and x minus 40. If I try to put the x's together though, I run into a problem. Because when I add 10x on both sides, that goes away and that goes away. And now I have -40 equals -40, and I no longer have an x. This is what is called a special case. And so let's talk about special cases, and let's figure out what this means. Okay, linear equations, which is what we have been solving up until now, they can have three types of answers. And once we learn about other types of equations, we'll learn what kind of special cases they have. They may be the same as this, they may be a little different. It depends on the type of equation. But our linear equations that we've been solving, they actually have three possibilities, although I purposefully have only given you one of these situations up until the challenge problem on 1.4. So the first possibility is that we get a unique solution. The word unique means one of a kind, or, you know, something that's not really repeatable, that kind of thing, right? So a unique solution is when we get x equals a number, and that's the only thing that works for that equation. When you solve an equation like normal and you end up at the end with x equals a number, you've got a unique solution. Even if you're like, this is the 5th time I've got x equals 1, that's not what we mean by unique, that, you know, you get different answers every time necessarily. It means there's only one number that works. As opposed to, there are equations that actually don't get an answer at all. And what we do is we have a special way that we kind of say that as mathematicians, we all agree that this is a great way to say it to get the point across what we mean. And that is the second option, no solution. When we're solving equations, we're trying to get solutions. So if we don't get a unique solution, we could get no solution at all. There's nothing that works for that equation. That's going to happen to us, and we're going to see how that happens. And the third one is that we could have infinitely many solutions. And in the case of linear equations in particular, that means that our solutions are actually all real numbers. So infinitely many refers to the idea that there's a lot, right? Too many to count. Infinite means too many to count. Infinitely many solutions means there's too many solutions to count. And that actually is because for these types of equations, you could literally pick any real number and it would work. And so that means you could pick 1, you could pick 10, you could pick 0, you could pick pi, you could pick you know, the grossest decimal or fraction that you possibly can think of, and it would work. It would fit into that equation and maintain equality between the two sides. So the second and third option here, those happen in cases like what we just had where our variable cancels out. And the next thing we do when our variable cancels out like that is we look to see if what's left is a true statement or a false statement. So we ended up with negative 40 equals negative 40. Well, that's true, right? Negative 40 does equal negative 40. When you get a true statement, that's going to be your sign that you have all real numbers as an answer. So you could write true statement. Okay, that means I'm going to write all real numbers for my answer. For no solution, we're going to see a false statement. So getting things like you get to the end and it says 0 equals 2. Well, 0 does not equal 2. So what that means is that no matter what number you plug in for x, you're not going to get a true statement, so there's no solution. So we are now going to do some examples of how to do this, and it's going to be a really good time. All right, example 1, we've got an A equation and a B equation. If you are guessing that one is going to be one type of special case and the other is the other type, way to go, you figured me out. So actually, most of the time our equations that are going to give us special cases will be more complicated than these, just because once you realize what you're looking for, it's really easy to tell that these are special cases. So for whatever reason, and I mean I do it too, it's more fun if it takes you like at least one step to be like, oh, this is a special case, instead of just knowing right off the bat. Maybe that's just me, I don't know. So in both of these cases, we could either we could go ahead and subtract 10x from both sides and then see what we're left with. So let's try that here. Minus 10x, minus 10x. Okay, so our x's cancel. That's what our red flag is as far as knowing this is a special case, is that, hey, those x's went away. Then we look at this and we say, Is that a true statement? Does negative 1 equal 2? No, it does not. And that means that we say no solution for our answer. Now, looking back at the beginning, if you have 10x minus 1 and 10x plus 2, hopefully, maybe not now, but maybe at some point you're like, well, wait, that totally makes sense why nothing works for that. Because if you're going to times something by 10 and do different things to it after that, well, how could you get the same number? If I times by 10 and then subtract 1, I can't get the same thing if I times by 10 and then add 2 as well, right? So at some point, maybe once you get to that step before you actually subtract, you'll realize that it's no solution. And then B, we can again do minus 10x on both sides and see what happens. But also, if we're really paying attention and looking, we can say, okay, wait, if I have 10x minus 1 equals 10x minus 1, if I pick any number I want to, doesn't that have to be true? 10x minus 1 will always equal 10x minus 1. And I almost feel like I should go back to a normal equation and point out, like, it's not so obvious that they're equal, right? Let's say if we have 2x plus 3 equals 7, right? Is it obvious that those are equal? Well, I would argue no. We have to do some figuring out. You may be able to figure out in your head. I'm not saying you can't, but it takes a little bit more effort to be like, yeah, okay, I can see how you can make 2x plus 3 equal 7. It's by choosing a certain value for x. Well, on B here, they're already equal. So you can literally put in anything you want and have it be an answer. Now, if that doesn't float your boat, if you still want to subtract 10x from both sides, I'm happy to do that, because then we get to do this thing where we're like, negative 1 equals negative 1. Is that true? Yes, it is. Now here's what we do to write our answer, is we say that our answer is all real numbers. And I tend to get students a bit complainy at this point, because they're like, do I really have to write out all real numbers? And I normally say, yes, yes you do. I would like for you to write out all real numbers, and I would like for you to write out no solution, because these are our accepted answers for these situations. That'd be super cool. Do it. All right, example 2. Now this is what I mean by them making it a little bit less obvious that we've got special cases going on. And so it might not even be true that these are special cases. Maybe I, tried to throw you off and they actually work out to be unique solutions. We won't know until we try, right? So we're going to go through the same process we did in 1.4 with multi-step equations, where we distribute to get rid of parentheses, we add like terms if we have them, and then we follow our order of operations for equations, which remember is not exactly the same as it normally is. So I'm going to start by distributing this 4 and get negative 20x, and then plus 4. Then I'm going to distribute this negative 2, so I get negative 20x plus 4. And as I said in the last one, this is the point actually where you could stop and say what the answer is if you realize it. If not, if you don't realize what the answer is yet, keep going and add 20x to both sides. And then that gives us 4 equals 4. Is that true? Does 4 equal 4? Yes, it does. So our answer here is all real numbers. If this, by the way, I don't know how much you would have heard the term all real numbers before at this point, but if you've ever heard this term and thought, does that mean there are some numbers that aren't real? That is a great question. And you know what? I'm not going to tell you, because you need to get farther in math first. Okay, all right, B. We've got this lovely equation that obviously looks completely tight and not at all like I messed up and had to change it and re-record. But it's fine. Let's distribute and do all that stuff. So 3 times 6x is 18x, and 3 times 4 is 12. Don't forget about this plus 1. Then we're going to come over to the other side and distribute the 2, so that we get 2 times 9x is 18x. 2 times 5 is 10. Let's add this perfectly normal looking 4. And let's continue. Let's do the 12 plus 1 and the 10 plus 4. So that's a plus 13 and a plus 14. It could be that this is the point where you know the answer. It could be you need to go a step farther. Either of those is fine. So, whichever way you do it, hopefully you can say now with confidence that because 13 equals 14 is not a true statement, there is no solution to this equation. Now you try. So solve these equations and see what you get. They could be special cases, they might not be, but pause the video, give it a try, start it back up, either when you have an answer or when you get stuck, so that you can get past where you get stuck, if that's what happens. Go. Welcome back. We're going to solve this first equation. There's nothing I need to do on the left because there's not a parentheses, but on the right I need to do 2 distributed into the parentheses. So 2 times negative 2x is negative 4x, and 2 times 1 is 2. And so we do have like terms here on the right side. I can add 2 and 5 together, so let's do a rewrite. And this could be the place where you're like, oh, I know the answer. Or it could be you decide to go ahead and add the 4x to both sides. And then we look at this, we ask ourselves that wonderful question. Is negative 7 equal to positive 7? And this is one that could trick you, because you could drop a negative and have them be the same, or you could just not be paying attention, or you could accidentally convince yourself that negative 7 and positive 7 are actually the same thing, which they're not. And you could pretty easily accidentally say this is all real numbers, but it's not. It's no solution, because negative 7 does not equal 7. Let's look at B. Distribute. Oh, if you were stuck on the first one and then you learned something, go ahead and pause the video, try the second one again. Let's see what we've got. So distribute. 6 times negative 4x is negative 24x. 6 times 2 is 12. Distribute on the other side. Negative 3 times 8x is negative 24x. Negative 3 times negative 2 is plus 6. So make sure you don't forget about this plus 6, especially if you distribute and then think that plus 6 is the other plus 6. You might forget about it. Anyway, so this is negative 24x plus 12 equals negative 24x plus 12. This may be the point where you go, I think I know the answer. Or it may be that you go a step further and add 24x to both sides. Either way is fine. So we get 12 equals 12, which is all real numbers. I am hoping that this seems pretty straightforward, pretty easy, because in some ways you get to stop the problem earlier, right? Because you can actually get to the point where you divide by what's in front of x, which usually is something that happens in our equations. So in some ways it's a little bit easier. Now normally you would have some of these mixed in with other equations so that it might catch you by surprise. So that's one of the ways this can be trickier. But I do have something that's going to help us in general with being more confident about our answers. And that is the idea that we can actually check our answers. I'm not going to go on a long-winded tangent about this, just a short-winded one, but one of the things I like most about math is that, for the most part, there's a correct answer that everybody can get to if they know what they're doing. We can check all of our answers when we're solving equations, and especially these linear equations we've been doing. It's super duper easy. Now, it can be tedious and feel kind of pointless, especially if you have solutions given to you by your wonderful teacher. So this is really more of a thing of we should practice it some just to make sure we can do it, but the time to use this skill is actually when you have high stakes of getting it right. So on something like a quiz or a test, you'd want to, go that extra step. And then the other time to use it would just be if something feels off about your answer. So, I don't know what that might be that feels off, but if something feels off, just throw it back in, see if it works. So we're going to do this. There's 2 of these. So starting with the first one, x equals 5, a solution to the equation 2x plus 3 equals 13. And I also think this might help us, if we didn't already understand what was happening here, to understand a little bit better. We're going to take the 5 and put it where the x is. This is where our warm-up is going to come in. And what it's asking us is, do these 2 sides actually equal each other? Because that's what's supposed to happen in an equation. They're supposed to be the same thing on both sides. So it's asking, is 5 the number that makes this work? And so we're going to work out the left side. 2 times 5 is 10, and then we've got 10 plus 3, which is 13. So yes, x equals 5 is a solution. If we work it out and it's not something that gives us an equality, then that would mean that that is not an answer. So if you do solve an equation and decide to check it and what you get doesn't work out, you need to go back and see if you can find your mistake. When you do that on a test though, if you get something and you're like, I think that's wrong, I would encourage you not to immediately just erase the whole thing and instead to move over to a different part to work it out. Because if you just end up not being able to get an answer, it's better to have work down to show the teacher you tried than to basically have erased all your attempts and then have a blank question, which then the teacher can't give you any credit for. Because every now and then you might get almost all of the points because all you did was a really silly mistake like multiplying wrong or subtracting wrong or something. But otherwise, everything about your equation was right. So, yeah. Okay. Is x equals 1 a solution to this equation? This one's a little bit more complicated on purpose because I do want us to think about order of operations, but the very first thing we're going to do is put the 1 where the x is on both sides. And this is an important skill in general. We don't just end up using this for checking our answers. We end up using this for other things as well. So we do what's inside the parentheses here. We do the multiplication and then we subtract the 1. So 2 times 1 is 2 and 2 minus 1 is 1. So I'm going to do 7 times 1 on this side. Here I've got 3 times 1, which is 3, and then I'm going to do minus 4, which, if you're not paying attention, you could actually get this wrong, right? 3 minus 4 is negative 1. 3 plus 4 is 7. So with wishful thinking, those would be the same, but they're not. 3 minus 4 is negative 1 because you're subtracting more than what you have. So that's not equal, right? So we would say, no, this is not a solution. Now, this doesn't tell us in the context of this problem anything else about the solution. It doesn't even tell us if there is a solution. We would have to solve it ourselves to figure that out. And I completely made this up, so I'm not even sure if this works out to a nice answer. So you may not want to, go down that road unless you just really want to. But that's how we can check our answers to see if we're right. On our worksheet, there is going to be some practice of this so that you can get the hang of it before some highly critical time like a quiz or a test. All right, it's that time again, challenge time, and nobody's answered any of my challenge questions, so I don't know if people like them or not, but I guess I'm just going to keep doing them until I get tired of inventing them. And just like this last time, this is going to be what we look at in the next lesson, the next video. So what do we do when we have an equation that has fractions, or if it has decimals? Do we do anything different? Do we do it the exact same way? Well, you'll have to look at that video to find out. But the short answer is yes. You can do it the exact same way. But we also do have something that we can use to make it easier. So it's like both of those were the right answer. I don't know, maybe. But give this a try if you'd like to. If you get an answer or just want to comment on it in general, that's what the comments down below are for. Hey, thanks so much for watching. I hope that you liked it. And if you do like it, you should like it, as in with the thumbs up button. Feel free to subscribe, comment, do all those cool things that YouTubers are always telling you to do, because I am in fact a YouTuber, believe it or not. That's why you're here watching me. I will see you in the next video, hopefully, on Algebra 1. You can check out my website for more resources. I'm doing a whole set of Algebra 1 curriculum with videos, notes pages, worksheets, solutions, and extra practice and everything. So definitely check it out if you'd like to. And thanks for watching. Bye. Hello and welcome to a new Algebra 1 video. This is lesson 6 and is either our last lesson for Unit 1, or I may do one more just for those that are interested in seeing some of the real-world applications of solving linear equations. But let's go ahead and look at this one. We are going to solve linear equations with fractions and decimals. And look, none of us want to be here doing this. Well, except for maybe that, that one kid. But we got to learn how to deal with it, because believe it or not, fractions and decimals are more often the norm in the real world than whole numbers. Just go in your house somewhere and measure like any piece of furniture, and you will be surprised at how hard it is to find furniture that is actually like a whole number length. I mean, at least I'm shocked every time I try to measure and find this out. So if you'd like to follow along, I have a notes page you can download, and that'll make it easier so you don't have to write down all the examples. And let's go ahead and get started with a warm-up. Alright, we've got a warm-up here, and this is gonna just kind of refresh our memories a little bit about fractions and decimals, because you know what, maybe you haven't had to do a lot with fractions and decimals recently. So we need to warm up. So pause the video and try these on your own, and if you have any trouble whatsoever, start up the video because I will walk us through them. Okay, I assume you're back now. We're going to look at this first one, which is adding 3 fractions together. What we need when we add fractions together is common denominators, and that can be easy to forget. We might just get confused about the rules, but we need a common denominator. Since we've got 3 fractions here, we're going to go ahead and try to get a common denominator for all of them. And so what we do is we say 5, 10, and 2. Is there a number that I can turn all 3 of these into? Or even better, is one of these a number that has the other 2 as a part of it? So 10 actually has a 5 and a 2 in it, which means that we could make all of these have a 10 on bottom really easily. The next best choice would be 20, if you didn't realize 10 would work. So to get all of these to have 10 on bottom, we think about what do I multiply by to get a 10. So for 5, I need to multiply by 2. And since I'm going to multiply by it on the bottom, I have to multiply it on top as well, because that gives me an equivalent fraction. So this one's going to turn into 4 over 10. 3 over 10 already has 10 on bottom, so it's good. And then we think, okay, what do I need to do to a half? I want it to have 10 on bottom. That's not what I meant to write. I want it to have 10 on bottom, so to do that I need to multiply by 5, because 2 times 5 makes 10. 2 to the top and the bottom, and so that changes it to 5 over 10. Now we're going to add these 3 numerators together. So 4 plus 3 is 7, and 7 plus 5 is 12. So we get 12 over 10. There are 2 things that we can do to our fraction answers some of the time. We can't even always do it, but we should always check to see if we can do it. One of them is to reduce the numbers to the simplest numbers we can get. Simplest meaning smallest. So 12 over 10, they're both even. They're both divisible by 2. So we're going to divide them both by 2 and get 6 over 5. That is an absolute must of a step. You need to always be looking for, can I divide them both by 2? Can I divide them both by 3? Until you get something that doesn't have anything in common. The other thing you can do that you can check for is we can change this to a mixed number. Although starting in Algebra 1, you are not really required to change things to mixed numbers unless your teacher specifies otherwise. So if you immediately went to this, you may have even done that actually before you reduced. But if this was like your immediate go-to answer, that's great. It is super helpful to know how to get mixed numbers out of improper fractions, but starting now, we kind of are like, yeah, improper fractions aren't so bad actually. They're easier to work with a lot of the time, so we just kind of leave them unless we have a reason not to. So 6/5 or 1 1/5 is our answer here. Let's look at number 2 down here. How do we divide fractions? So we do 4/7 and then we switch it to multiplication. I've heard like a catchy phrase like keep, switch, flip. So we keep the 4/7, we switch it to multiplication, and we flip the 1/14. We get its reciprocal, and then that lets us multiply these together. When we are multiplying fractions together, we can check for things to cancel before we multiply them, because I don't really want to do 4 times 14 if I can avoid it. And if I notice that 7 and 14 are both divisible by 7, then I can cross them out. And then I've got 4 times 2 on top and 1 times 1 on bottom, which is 8/1. Now, you do need to write 8/1 as 8, because that's just, it's silly to leave it as over 1 whenever it doesn't have to be over 1. That's different than the idea of us changing things to mixed numbers. We do simplify things like 8/1, 8/2, things that divide evenly, we do go ahead and do that. How about if we are adding decimals together? So the important thing is to line up the decimal. So this is 0.1, we line up the decimal, and it might help us if we go ahead and put a 0 there at the end as a placeholder. And then we've got 0.24, and then we add in our columns. So 5 plus 0 plus 4 is 9, 3 plus 1 plus 2 is 6, so this is our answer. And then when we're multiplying, we take the longer number, it doesn't necessarily mean it's bigger, but the longer number, and put it on top, and then we take the shorter number, put it on bottom. These zeros at the front that I keep writing, we do not have to write, and whenever I was a student, I did not bother writing them, honestly, but I like to write them now because I think it makes the decimals look nicer. But we don't need to multiply with those zeros. We just need to do basically 5 times 17 here. So 5 times 7 is 35, and 5 times 1 is 5, plus 3 is 8. Then we look at how many decimal places there were, because that's how many our answers need. And we look at, we add up the decimal places. So there's 2 decimal places here, and there's 1 here. So our answer needs 3. So we have to add a 0, so that we have 1, 2, 3 places. So our answer is 0.085. Now, I'm doing this, you know already that this is going to be solving equations with fractions and decimals. So at this point, you may be worried, because maybe this did not go smoothly for you as a warm-up. That's fine, that's okay. Fractions and decimals do make everything more difficult. So here's the thing. We've got 2 ways to approach these problems, okay? One of them is just to go for it, like what we've been doing. Get the x's on both sides, get the numbers on both sides. When there's fractions, make sure you get common denominators when you need to, make sure you divide the right way. Same with decimals, make sure you add correctly, make sure you divide correctly, okay? But there's another way to do it. Okay, the other way to do it is to get rid of the fractions or decimals as your first step. And it almost feels like it's cheating the system, right? Like, the whole point is that these have fractions or decimals in them, and you're saying get rid of them. Now, there is a correct way to get rid of them. You can't just just erase them or something. But that is likely to be the best way to do it, is just by not dealing with them. Get rid of them. You don't have to. So if you forget, you can just try to do it a normal way, where you add the things over and subtract and divide and all that. But we're going to walk through how to do this for a few examples, first for fractions, and then a few for decimals. And then I've got a practice page that you can practice this on your own to see if you've got it. Alright, so the way we're going to approach this is we are going to get a common denominator for all of the terms that we have. So whether they end up being fractions or not, actually, we're going to look at basically each of these terms. So this is a term, this is a term, this is a term, and this is a term. We're going to look at each of these terms and say what would be the best denominator to get, and then we're going to get it so that everything has the same denominator, because once everything has the same denominator, there's something super cool that we can do to make this way easier. So it looks to me, since we got 2, 4, 4, and 8, that the best denominator would be 8. The next best denominator would be 16. So keep that in mind. If you thought 16, that is the next best choice, and it's better to pick something than nothing. So I'm going to pick 8 though, because it's the smallest one that we can get. And I'm going to look at this 1/2 and say, okay, how do I turn that into an 8 on bottom? Need to multiply by 4 on the top and the bottom. So that turns that fraction into 4/8. And then I just keep going. How do I change this 4 to an 8? Times by 2. So that gives me 6/8. Same with this 4, I need to times by 2. You just got to make sure to change the top as well. That's one of the easiest mistakes to make. So 2/8x plus 7/8. So here is the amazing thing that we can do to make this easier. If they all have the same denominator, then we can just get rid of the denominator. And here's why. We could, and you can skip this explanation if you're like, I don't care why, I'm glad that we can do it. But we could, our next step could be that we have these x's, we think of them like they're on top of the fraction instead of next to it. That might help us out. And then we'd say, okay, we've got 4x plus 6 over 8 equals 2x plus 7 over 8. Well, here's the deal. If they're both over 8, then it has to be true that the tops equal each other. So that's why once we have a common denominator for everything, we're allowed to just say, hey, we don't need it anymore. So our next step is going to be to write 4x plus 6 equals 2x plus 7, and then we're going to solve like normal. There's a higher chance of these ending up being fractions just because they're harder to make work out nicely and also do all the things I wanted them to do. Also, my hope is to kind of get us used to that as being okay. If you are ever like, well, here we go, I got 2x equals 1, I divide by 2, should I write this answer as a fraction or a decimal? First thing is to look at the instructions and see if they ask you to do it as a fraction or a decimal, which these instructions just say solve, they don't ask us. Second thing to do is to say, okay, they gave me fractions, I should put my answer as a fraction. Whereas if they gave me decimals, I'd want to put my answer as a decimal. If I have whole numbers in general and then I end up with an answer that's not a whole number, then it's kind of your choice, but I think most teachers prefer that we leave them as fractions, and actually it ends up being easier to leave them as fractions even if you don't like it as much, because in order to write it as a decimal you have to divide and that can be an unpleasant experience sometimes. So if we leave it as a fraction, we don't have to do that. So our answer here is x equals 1/2. So now that you've seen it, you may be able to kind of work ahead a little bit. So I've got an example 2, and then I've got a now you try. So you might think about at least trying to predict what our common denominator is going to be, because that I think is something that we get tripped up on and makes us just not even want to start. And then go through the rest of the problem with me and see how it goes. And then try it all by yourself on the now you try. Then we'll go to the decimals. Alright, example 2. So we've got fractions. Let's think about what our best denominator would be. We have a 6, a 3, a 2, and another 3. Now we can turn all of those into 6. Now again, it may be that you didn't come up with 6. You may have come up with 12, which would work, or 18, which would work. And those are fine. You should totally do something rather than nothing, right? But 6 is the smallest denominator that we can have, which will make our numbers the easiest to work with. That's why we like the least common denominator as opposed to just any denominator. So since I want these all to be 6 on bottom, this first one is fine as 5, 6. The next one, 3, on bottom, we times by 2. And that gives us 2 over 6. Now we are going to do the 1/2, so we need to times that by a 3 to get it to be 6 on the bottom. So 3/6 x. And then the 2/3 needs to be multiplied by 2 on the bottom. So that gives us 4/6. So now that everything has a 6 on bottom, we get rid of all of the denominators and say this is just 5x plus 2 equals 3x plus 4. And then we just do our cool equation solving things that we've been doing for a few lessons now. 5x minus 3x is 2x. I'm going to subtract the 2 over here and get 2. I can't believe these both ended up being whole numbers. It really is a lot harder to get whole numbers here when you're making these up. Oh wait, the first one wasn't a whole number, it was a fraction. It just was a nice fraction. Now you try. So this one is a little bit different, but I want to encourage you to pause the video and then start it back up either when you get done or when you get stuck. And if you're getting stuck, just kind of play the video a little bit at a time. Every time you get unstuck, try the problem a little bit more, and then if you get stuck again, play the video again, and so on. So pause. Welcome back. We are going to get a common denominator here, and what's different on this one that could throw you off, by the way, is that we've got a whole number here at the end. We want to start off by making that a fraction. All whole numbers can be fractions by putting them over 1. And we just don't write them as over 1 because we're lazy and because it's just not necessary. But this helps us remember that everything needs the same denominator, including our whole numbers. If you forget and just like leave the +4 as a +4, you're going to end up with the wrong answer, because the only way that our trick of dropping the denominators works is if everything has the same denominator. So I want to get a 10 on bottom of everything. 20 would be our next best choice. I'm going to take this 5 and times it by 2 on the top and the bottom, so that I get 6 over 10x. 7/10 already has a 10 on bottom, so I don't need to change it. And then this -1/2, doesn't matter that it's negative, I just need to think about how do I change this denominator. I'm going to times by 5. I do keep it negative. That still needs to be a -5 over 10. And then how do I change 4 over 1 so it has a 10 on bottom? I have to times by 10 so that I get 40 over 10. Now let's drop all of our denominators and finish. 6x minus 7 equals -5x plus 40. So I'm going to add 5x over to this side, and I'm going to add 7 over to this side, and this gives me 11x equals 47. Now this is an example of a truly terrible looking fraction in my opinion. Now you might say, hey, just like we don't judge books by their covers, we shouldn't judge fractions by their unfortunate numbers. And you know what? You're probably right. We probably shouldn't. But this is our answer, 47 over 11, because 11 does not go into 47 evenly. We could change it to a mixed number if we want to, but we don't have to. So that's our answer. Now let's figure out how to do this with decimals. Example 3. Now we're on to decimals, and it's going to be a little bit different, but also kind of the same. Let's see if you see what I mean. We have, if we look at this, each of these different terms has a single decimal place. They're all tenths places. So what we can do is we can use a power of 10 to basically move all of these decimals so that they're not going to be decimal places anymore. We're allowed to do this because of that property that we went over a few lessons ago, the multiplication property of equality, that as long as we multiply every single thing by the same number, then it is still the same like equation that we had before. So since all of these are have the tenths place, we're going to multiply by 10. So think about it. When I multiply by 10, it moves my decimal one place over. Sorry, it's going to be backwards for you, so it moves it one place over. Anyway, we move the decimal over the same amount for each to the right, and so that's going to make this be 2x, because we're multiplying this whole thing by 10, and so everything gets multiplied. This is going to turn this into a 7. Going to turn this into -3x, and this into an 8. Again, we have a higher chance of getting a fraction or decimal answer on these, although I do think I tried pretty hard to make them work out nicely. 2x plus 3x is 5x. And then I'm going to subtract the 7 over to this side. So 8 minus 7 is 1. So we're going to divide both sides by 5. And you see we do get something that does not end up being a whole number. And like what I said earlier, since these started off as decimals, it would be nice if we had our answer as a decimal. Like whatever they give you, whatever kind of numbers they give you, our goal should be to give them the same kind of numbers back. So what is 1/5 as a decimal? You may know that off the top of your head, or it may be that you come over to the side and do a little division real quick. And so this is why leaving as fractions is way better, because if we leave this as a fraction, it's just 1/5. Well, let's go ahead and get the decimal. So you say, okay, 5 goes into 1, nope. 5 goes into, and then we kind of ignore the decimal and say 5 goes into 10 twice, and it goes in evenly, so we're done. This was actually pretty nice, and it's 0.2. And that's our answer. Let's try another one. Okay, so in this one, we're going to get rid of the decimals again, but if we look, this last one has 2 decimal places, not 1. So if we really want to completely get rid of our decimals, we're going to have to move everything over twice, not just once. In other words, it's like we're multiplying by 100. Now, if you decided to just multiply by 10, that would actually still make this way easier than it is right now. So that is an option. And maybe that's the way you decide to go, because multiplying by 100 is going to make us have some big numbers here. So it's kind of, you pick your battles. So for this 1.7, we're going to move the decimal over to the right twice. So 1, 2, we need to put a 0. So this is 170. And then 1, 2, this is going to be 20 minus 20. 1, 2, and get 210x. And then this one and this one, minus 25. So now we're ready to solve. So I'm going to subtract 170x over here. I'm going to add 25 over here. So I have 5 equals 40x. And divide by 40. So if I simplify 5 over 40, I divide them both by 5 and get 1/8. Even though we are going to end up trying to write this as a decimal, it is easier if we have smaller numbers to work with. So it's still a good idea to do that. I'm going to put 8 into 1. If you're asking yourself, why are we doing this? Why aren't we just leaving it as 1/8? You don't have to change it, but you do want to watch out for instructions that tell you to change it, and it would be considered kind of like best practice for us to give our answer the same way that we got the question, which is decimals. 8 goes into 20 twice, minus 16. And if you're worried this is going to go on forever, 8 into 40 goes in 5 times. So our answer is 0.125. All right, now you try. So pause the video, see how far you get, start it back up when you're stuck or when you've got an answer starting now. Welcome back. We are going to multiply everything by 10, and that's because the most decimals any of these have is just 1. None of them have 2 decimals or 3 decimals or more than that. So we're going to times by 10. Now we do have a 6 here at the end that still gets multiplied by 10. We don't skip over it or anything, because then we won't have multiplied everything by 10. So 10 times 2.1 moves this over once, and we get 21x. 10 times negative 0.3 moves this over once, so we get minus 3. Then we move this over and get negative 7x, and this over gives us 60. So then I add 7x and get 28x. I add 3 and get 63. Again, because I'm looking at this, I'm like, this does not divide evenly, but if we notice something that goes into both, it is helpful to simplify. these are both divisible by 7, which isn't easy to see necessarily. This turns into 9/4, which is actually a really relatively easy thing to know what it is as a decimal. And since we're changing to a decimal, you might decide to go ahead and change to a mixed number because maybe that's easier to work with. 2 1/4 is 2.25 as our answer. So if we didn't go through that process or know that off the top of our head, we just go over to the side and do some division like we've done in the earlier ones. Thank you for watching. I hope that you'll subscribe, like, comment, all those cool things, and I hope that you'll check out the next video whenever it drops. And I hope you have a great day and that all of your math problems get solved. Bye.
Hey there, welcome to lesson 1 of Algebra 1, solving one-step linear equations. Pretty excited for us to get started with this. So I'm creating my own Algebra 1 course. That's my goal right now. So I've got Unit 1 is all about solving linear equations. And at first some of this might be familiar from pre-algebra. Like, it's quite possible you could skip this lesson entirely depending on how well you did in pre-algebra, but I encourage you to just sit and try to absorb. I have a notes page on my website that I'll link down in the description that you can go to and print off and follow along, and it gives you some good practice on notes and following along and that sort of thing. But I'm also hoping to kind of give a good foundational perspective on how solving equations work with these really simple equations that then we can build on once we get to more complicated equations. So get ready. Here we go. First thing I would love for us to do is actually a warm-up here. And on this, the idea of a warm-up is both to just get your head in a math mindset, but also a lot of times it has a direct tie-in into what's going to be happening on the lesson. So not all the time, sometimes it's just a way for your teacher to basically encourage you to get in and start being quiet and that sort of thing. But I always try to make it connected somehow to the lesson that's about to happen. So you might have a sense of foreshadowing coming up here. So check out these questions. We've got basically words that are describing some math that's happening, and we're supposed to be trying to figure out the answer. So if you would like to pause the video and see if you can come up with the answers, I think that's a great idea. So I'll wait here. Alright, let's go through these and figure out the answer. So number 1, what number plus 10 equals 14? So think about that. We've got something that when we add 10 to it, we get 14. Do you know what the answer to that is? It is 4. Number 2, what number divided by 2 equals 8? Okay, so you got to think in your head, got a number, I'm dividing it by 2, it gives me 8. So something divided by 2 gives me 8. That's going to give us 16. So that would be our answer. And notice we had this word plus, we had this word divided by, or words. We have these words equals, that all of those are telling us operations that we should be doing. So that's super helpful to be able to translate that math talk into, or translate English words into math. Yeah. Number 3, if the sum of a number and 7 is 11, what is the number? Gotta love when 7 and 11 are put together because they rhyme and because there's a, yeah, never mind. So something, we're talking about sum, so that's addition. So we have a number and 7 added together is 11. So what does it take to get from 7 to 11? How many is between there? That's also 4. Coincidence? Yes, entirely. I did not mean to have that happen. So that's our warm-up, and this is going to lead us directly into our topic of the day, which is solving one-step equations. Now, before we get too far into this, let's actually talk about what an equation is, in case you're not super familiar with that term, because it's going to be kind of a big deal for the rest of math, and in particular any class that starts with the word algebra. So an equation happens when you have two expressions that have an equal sign between them, and it's showing that this thing that's on the left side of the equal sign and the thing that's on the right side of the equal sign, that those are equivalent, that they are things that are replaceable. So kind of like if I had my name equals mom, those are interchangeable, right? Because I have my own actual name, and then I have the name that my child calls me. Those are equivalent names, sort of. That's not necessarily a great example, but it's this idea that we want to show that this equals this, so we put an equal sign in between and it becomes an equation. So another way of saying that, a statement that says two expressions are equivalent in value. So the warm-up, those sentences or statements were actually giving us two expressions and saying that they were equivalent in value. If you're unfamiliar with the word expression as well, an expression in math is just a collection of numbers, letters, operations that don't have an equal sign. That's the big difference between an expression and an equation. And then equations are kind of a big deal in algebra, so be prepared to see a lot of them. There's so many equations. It's just basically all of algebra just about is equations. All right, now that we know what an equation is, what is a linear equation? So the word linear there refers to equations that can be represented by a line. So that should be an easy connection to make, because the first four letters of linear is the word line. And there's ways that we can tell by looking at an equation that it is actually a linear equation, that we could represent it with a line. And we will look at how the equations go with lines more in the next unit. We'll actually do this thing called graphing, where you make equations show up visually, but we're not quite there yet. We're going to do a bunch of solving first before we get there. So the way we can tell just from the equation that what we have is linear is that it needs to have at least one variable. Otherwise, I mean, I guess it could be an equation if it doesn't have a variable at all, but that isn't an equation that would be very helpful to us, at least not in algebra. So it needs to have at least one variable, but it can actually have a whole bunch of variables, different letters, and still be considered linear. The most important thing about those variables is that they all need to be to the first power. And the interesting thing about that is that when variables or numbers are to the first power, we don't actually write their power, right? So if you have an x in your equation, it's to the first power, even though we don't write that one there. And that has to do with the fact that mathematicians, as well as all of humanity, are lazy by nature, and so they don't want to have to write more than necessary. And the one that is the exponent, as well as the one that would technically be the coefficient or the number in front of x here, we don't normally write those unless we need to write them for our own understanding for some reason. So if you see an equation that just has x without an exponent, it is to the first power. So what would tell you that something was not, in fact, linear would be seeing something like x with a 2 after it. That would make it not linear. Another thing that could happen is having an x on the bottom of a fraction instead of on top of a fraction, or really anything else that seems particularly weird. Like having 1 over x does not represent something linear. Or having a square root sign and having an x inside of that, that is not something that is linear. So we're just not really going to encounter those things much yet, or maybe not even at all this year. X squared, yes we will. But those other two situations will be a lot farther down the road for us, so that it should be fairly easy, hopefully, to see, okay, x or y or whatever letter I have, since it's not to a power and it doesn't look funny, then this must be linear. And why we care so much about linear equations is they are the simplest type of equations, so we're going to learn about them first. And the rules that we apply to linear equations also are the rules that apply to all other equations. And so it's going to help us build a foundation of knowledge that then we can apply to other types of equations as well, which is really helpful. Also, lines and linear equations come up a lot in the real world. There's tons of things that can be represented with a linear equation, and what's really funny is that whenever people are modeling actually really difficult things that are not lines, they'll sometimes actually still try to use lines to represent them just because of how much easier it is to use lines than anything else. And that idea is that if you have something that's a curve, for instance, like the Earth, and you zoom in really far on that curve, if you zoom in far enough, all of a sudden it looks not curved. It looks like a line. So the same idea there, that we can take relationships that are not linear, that are very curvy, and if we just look really, really closely at them, we can still actually think about them as a line. That's probably more information than you needed right now, but that's okay. Let's actually look at some equations. As I mentioned earlier, I've got a website with resources, and so if you would like to be following along with this without having to write everything down yourself, please head over there, link in the description, and you can print off a nice looking notes page for this. It's really important as you're doing math to write things down. There's some muscle memory things that happen that there are studies that show that writing things down and taking notes helps you remember things more than just sitting and absorbing. There's also the idea that you could look back at your notes and use them to help you complete assignments or to study for tests and things like that. And just in general, it's a really good habit. As I go through this, am going to attempt to mimic what I actually would do if I was solving it myself. I'm going to attempt to think out loud and hopefully help you realize what you should be thinking as you do these problems. And so by getting in that mindset of sitting here and writing down as I write down, that can be super helpful. I say all this, and this first example maybe doesn't have a lot to write down because we are starting off with kind of the simplest equations that are possible to solve. So as I look at these, there's more than one way to do this, and I actually want us to use mental math. So just like what we did in the warm-up, I want us to sit and think about the answer. So as I look at A, like point A, like the first equation, which is labeled with an A, it says x plus 3 equals 9. And so in our heads we could think, okay, what's the thing that should be there? Variables are representing a number. We may not know what that number is, but that's the idea. There should be a number where x is that makes this make sense. So what plus 3 equals 9? And hopefully, through thinking about that, you can pretty easily come up with the answer, which is 6. And we'll just go through the rest of these and see if we can do the same thing. So, because it's an equation, actually, we'd write x equals 6 to say, hey, you asked me what x is, and now I've told you x equals 6. On B, a minus 2 equals 10. So there's a number that we should be able to put here that when I subtract 2 from it, gives me 10. So think about it, and if I'm telling you the answer too quickly that you need more time to think, then make sure to pause the video as we're going along. If on the other hand I'm going too slow, there's a cool feature on YouTube where you can speed videos up so that I could be a lot faster if that's what you're into. So something minus 2 equals 10. That should be 12. Alright, let's look up here at C. When these are right next to each other, this is indicating multiplication. So 4 times y equals 20. 4 times what gives us 20? That would be 5. And this last one might be the hardest just because it looks like a fraction, which is intimidating. But what number, when you divide it by 5, equals 6? The answer to that is 30. Now, how difficult those equations were may depend on just how good you are at mental math, or it may depend on how long it's been since you did math, or things like that. But I think most of us who are at an Algebra 1 level of math should be able to, by exerting some amount of mental work, should be able to say, okay, I can figure out what number should go where this variable is. But these are the simplest equations possible, and they definitely get harder in such a way that maybe it's not always a great idea to try to just mental math your way through an equation. And so what we have are some really great algebraic properties of equality that we can use to help us figure out how to solve an equation. And they're all very similar. And since you're in Algebra 1, I'm assuming this may look intimidating, this slide, especially the middle where we've got a whole bunch of letters and no numbers. And what I want to encourage you to do is not stress out about whether or not you understand it. Listen though to my explanation, because throughout math, your textbook or maybe the notes your teacher gives you will have things that look like this. And I think the best way to start getting used to and understanding what they're trying to tell you is by continuing to be exposed to these sorts of things, hopefully with somebody there to explain what's happening. So these properties of equality go with each of our operations that we know and love, that we've been learning about for the last however many years that we've been in school: addition, subtraction, multiplication, and division. And each of these properties is actually saying a very similar thing, that if you have an equation, so in all three of these on the middle column, it has if A equals B. So if you have two things that are equal, then the next part is a little different on each, but each of them is saying as long as you do the same thing to each side of the equation, what you have is still an equation. So think about what that means. If you have an equation and you decide to just put a number somewhere in that equation that wasn't there before, you no longer know that those things are equal. In fact, they probably are not equal anymore, unless you add 0. You can add 0 as much as you want. But because we have these relationships, we're showing that this equals this. If I just decide to put an extra 4 somewhere, that completely changes what's going on. What this is saying is that if we do that thing to both sides of the equation, then we still have the same equality as before. And that gives us this last column that can maybe be an easier way to think of it. So the addition property of equality says you're allowed to add a number to both sides of the equation. The subtraction property of equality says you're allowed to subtract a number from both sides of an equation, and so on and so on. There are other properties of equality as well, I think. I feel pretty confident about that, but these are the ones I wanted us to look at least right now. So now that we've talked about this, we're going to go back to that example, and we're going to think about how can we use these properties to solve instead of just using mental math. So those algebraic properties of equality can help us here by helping us figure out a way to actually isolate the variable that's happening. That's a word that we use a lot in math. We want to isolate or solve for the variable. We want it to get it by itself on the side of the equation it's on. So here's the algebraic way we do this as opposed to the mental math way we did it before. I look on part A and I say x plus 3 equals 9. Because I have x plus 3, what would be super helpful would be if I could subtract that 3 away. That would be the opposite operation to plus 3, and plus 3 and minus 3 together make 0, meaning there will no longer be a plus 3 on this side. So depending on your teacher that you have, which is me right now, they might write this different ways. Because I'm lazy and don't like to rewrite things, I write minus 3 underneath right here. I say I'm lazy and that's why I do it, but I also like the way this looks. The properties of equality say if I minus 3 over here on the left side of my equal sign, I better also minus 3 on the right side of the equal sign. And then I like to draw a line underneath that. Then we do this thing that I think a lot of people find super satisfying. We say plus 3 minus 3 is 0, so we are going to just mark through those. They're not there anymore. That leaves me with just x on the left because that plus sign wouldn't need to be there either. You could write x plus 0, but that is writing more information than you need, because if you add 0, it's still x. So this would be x equals 9 minus 3, which is 6. Is that the answer we got before? Probably. Yeah, that's what we got before. And if you think about what you did mentally to figure out that you said, what plus 3 equals 9, whether you thought about it or not, you came up with that with the idea of subtraction in mind. You had to say, okay, I've got 3 and I've got to get to 9. What's the difference between those two numbers? Difference, by the way, is a word that means subtraction. So, x equals 6, and we did that using algebra now instead of mental math. Whoops. Alright, let's look at B. So here we have a minus 2 equals 10. So because we have a minus 2 there, now wouldn't it be great if we could add 2? So this is a situation where, hey, wouldn't it be great if we could add 2, but oh wait, we can if we use the addition property of equality. So I can add 2 here, and I can add 2 there, here are 2, there are 2, everywhere are 2, 2. I'm so sorry that I have a 3-year-old and you get nursery rhymes instead of rap songs right now. But I'm not sorry I have a 3-year-old, but I'm sorry that that's coming out in this video. Love you, 3-year-old. 10 plus 2 gives us 12, which is the answer we got earlier. And so I said earlier, as I'm going through this, I'm trying to mimic what I think you as a student should do. So these things I'm writing down, we call this showing our work. And yes, earlier we were able to just write down our answer without having to write anything else out. But by writing these things down I'm showing other people who look at this what my logic was. And so what's cool about this is it lets teachers or parents or whoever is looking at your work, it lets them see if you get it wrong, if there's a good, like, why did you get it wrong? So if you wrote down your work here on B and then said A equals 13, everything else was right, you just wrote 13 instead of 12. Well, that's an issue with, you need to be more careful about adding 2, because 10 plus 2 is 12, not 13. Whereas if all you do is write down the number 13 without any other work shown, then the teacher or parent or whoever is looking at it has no idea why you picked the number 13. The number 13 could have just been a completely random guess on your part, for all they know, if you don't show work. So teachers go on and on, math teachers go, and science probably, go on and on about showing work so that they can help you basically understand things better. And also it makes it look less like you just copied down answers from your friend. So 2 good reasons to show work. Part C. So earlier when we did this, we said this is multiplication. 4 times y equals 20. The opposite of multiplication is division. So we're going to use the division property of equality to divide both sides of this by 4. And get y equals 20 divided by 4. Again, this is essentially the same thing we did earlier. We just did it in our head earlier. When you think 4 times y equals 20, you are basically thinking either about your multiplication tables, or you are thinking, okay, well, I'm basically dividing by 4. So 20 divided by 4 is what? It's 5. So we were doing the same thing, just we maybe didn't realize that that's what we were doing. And then on this last one, which again, for whatever reason, I know that fractions just naturally have a tendency to seem scarier than other things. What's happening when we have a fraction is division. And so if we're doing n divided by 5, what we want to do to get rid of that 5 from the bottom is multiply both sides by 5. And so I left myself a small amount of room here to write times 5. But we're going to use the multiplication property of equality and do it to both sides of our equation. So what's really happening is that this is 5 over 1. And if you remember how to multiply fractions together, these 5s cancel out. And that's why that's the helpful thing to do here. And that means n equals 30. So that would be our answer. Okay, now it's your turn to try. So let's see if you've got the hang of this or if you need more explanation. And it's totally fine, by the way, if you need more explanation. People get things at different rates. What's important is that you keep with it. What we're trying to do here is we are trying to internalize these equation rules so that they become second nature to us. And that requires you doing enough problems to be able to say, oh yeah, I feel like I've got the hang of this and know what I'm doing. And the only way to know that is to actually try problems and then find out if you're right, preferably immediately instead of having to wait a while to find out. So, pause the video and give these a try, and then start the video back up when you are ready for the answers. Assuming that you did what I asked and paused the video and now have the answers, I'm going to go through and show my work and show how we use the proper